So today we have a lineup of terrific speakers, both senior and junior scientists, and the schedule is shown here. We'll first have a talk by Simon Barry from AstraZeneca, and then we have 5 talks before the next break. So I just would like to welcome Simon Barry, and Dimitri will do the introductions.
Yes, it's my privilege to introduce both keynote speakers. Today, I'm very happy to do that. Simon Barry is Executive Director and Head of the Tumor Microenvironment at AstraZeneca, been there for many years. Were involved in development quite a large array of small molecules targeting different aspects of immune system and myeloid cells in particular. Many people who work in myeloid cell field use the drugs which he has been participate very actively in developing, especially CXCR2 inhibitors and so on. He accumulated enormous amount of knowledge about positive expectations and failure of the different myeloid cell targeting strategy. And today his talk is entitled Opportunity and Challenges for Myeloid Cell Targeting Drugs and Cancer. And I think it will be quite educational for all of us. Simon, thank you for joining us today. And the floor is yours.
Thanks, Dimitri, and thanks for the invite to present. Just make sure you can see. Can you see my slides?
Yes, but
yeah.
No, that's perfect.
Brilliant. So, what I'm going to talk to you about today is a reflection on our experiences within AstraZeneca to trying to develop small molecule targeting drugs to inhibit myeloid cells in the context of cancer, and try and highlight to you some of the challenges that we face and present to you a case study of a retrospective analysis of our efforts on CXCR2 and where we think possibly we may have been able to make improvements to our development programs and how that might have implications for the new targets that we're bringing forward in the next wave of therapeutics. So there's many approaches that many of the people on this call have developed and identified to target myeloid cells, which obviously we're now trying to exploit to improve disease outcomes. So we can look at repolarization of PM and MDSCs or macrophage-like cells in the tumor. We can block the migration of these cells to the tumor. We can inhibit the suppressive activity of different features of these cells once they're within the tumor. And conversely, we can use mechanisms that activate good myeloid cells to overcome the impact of bad myeloid cells within the tumor. And all of these have been elegantly shown to be potential therapeutic mechanisms in different preclinical models. What I'm going to focus on is the molecules where we've done the most clinical trials and try and can you see this banner that comes up and down, by the way?
No.
No, cool. And focus on the trials, focus on what we've learned from these, and then my case study will be on CXCR2, as I mentioned. So we look at CSF1, CCR2, and CXCR2 inhibitors. There's been a whole host of molecules that have been developed to late-stage clinical trials, phase 2. A total of 39 clinical trials for CSF1 inhibitors, 6 for CCR2, 12 for CXCR2 inhibitors. Quite a lot of these in phase 2, so these are reasonably big investments. And actually, if we look at the efficacy that we've observed with these molecules, we have managed to be successful with CSF1 inhibitors, which is fantastic because multiple antagonists are now registered for tenosynovial giant cell tumor disease, which is a benign macrophage-driven tumor that's as a result of CSF1 overexpression to a splice variant. But there's been no other really strong clinical signals with these inhibitors in combination with chemotherapy or checkpoint inhibitors. CCR2, again, there was a study that demonstrated promising clinical signal with a Pfizer molecule in pancreatic cancer in phase 2, which was published in Lancet Oncology. But again, there's not been much work to develop CCR2 inhibitors into appropriate combinations, again with either chemo or with checkpoint inhibitors. And our own experience developing CXCR2 antagonists is that really we haven't seen any really positive data in the clinical trials that we've performed to date. So one of the things that we've asked for these inhibitors is, well, why were these approaches not more successful given the level of investment that we've made across many companies in trying to develop them? So looking at CXCR2, many people will be aware of that, so I'll run through this very quickly. But CXCR2 actually came onto our radar originally as an angiogenesis target back at the turn of the century. So it does have an impact in controlling endothelial cell biology. It also at the time was thought to have a role in controlling chemotherapy resistance and metastasis in the tumor cell compartment. And in the inflammation field was known to be a primary target for regulation of neutrophils and aspirin COPD. This is our history or timeline of work on CXCR2 and in particular our asset 5069 from an oncology perspective. So we started working on this target back in 2001 as an angiogenesis target, and we were quick to devalidate that as a meaningful way of targeting tumor angiogenesis. But over a period of time using tool molecules, we found that CXCR2 was indeed playing some role in chemo resistance, wasn't very convincing in vitro, but more convincing in vivo. And we found that by using knockouts in standard models, that clearly neutrophils were impacting tumor cell growth and survival in vivo, that we then used the molecule to try and elucidate in more detail. And it wasn't really until Bristol Hall's group started to publish the initial studies on depleted neutrophils priming IO that really the field started to get a little bit more attention internally. In parallel, we'd taken the decision to work with Owen Sampson and Jen Morton up at the Beats and to move beyond syngeneic models and start to position the biology in the context of gem models. And using AZD5069, which was the only molecule that we found that really had the legs to tackle the target in humans, we then started to develop platforms of evidence, as we call them, within AstraZeneca to make a case for trials in pancreatic cancer, in prostate cancer, in collaboration with Andrea Alamonte. In head and neck cancer, we initiated a trial, and also a platform for colorectal cancer and hepatocellular cancer, all in combination with either chemotherapy, checkpoint inhibitor, or in the case of prostate, to prevent androgen resistance. And these preclinical studies that we invested in, which took many years to develop and deliver, resulted in 4 trials: SCORES, which was head and neck; Everest, which was a pancreatic trial with durvalumab; ACE, which was a prostate trial with enzalutamide in actively progressing patients; and then a trial that's now ongoing in Newcastle and Glasgow, which is a HCC trial specifically targeted to fatty liver-driven HCC, which is a trial called CUBIC in combination with durvalumab again. As I said before, CXCR2 was sort of well tolerated at the doses that we gave it at, but actually there was no signals really reported in these small phase 2 trials of up to 20 to 30 patients. However, what we did understand do while these clinical development programs are ongoing was develop our understanding of the biology, which you could say is a good thing, it's a bad thing, but it's taught us a lot when we go back and relook at the data. One of the things that was really important with AstraZeneca over the years for the tumor cell targeted drugs was this concept of the 5 Rs, which have been published in these 2 papers from Mane Pangalos, which was to look at right target, right tissue, right safety, and the right patients. And we went back and used this framework to sort of do a retrospective assessment of where might we have gone wrong in assessing 5069 CXCR2 biology. And in particular, we focused on our evidence for our link between the disease and target, the biomarkers that we used, the concentrations or the exposure relationship we had between 5069 cover and target inhibition, and the PK/PD relationship in the clinic, as well as the safety and the other issues that we may have around the target as a liability in terms of safety issues. The studies that initiated our pancreatic trials were ones that were published back in 2014 by Colin Steele and Jen Morton. where we showed that CXCR2 clearly played a role in facilitating metastasis in pancreatic cancer. These were late-stage KPC models where we showed alone and in combination with gemcitabine that there was a reduction in metastases and that actually there was an overall survival benefit when combined with gem. We were also able to show in these studies that a subset of mice got quite durable responses with checkpoint inhibitors, and actually for very late-stage disease, combining with PD-1 was also of significant benefit in these particular models. That triggered the trial that we performed. This role in metastasis, our confidence in this observation of role in metastasis, was further underpinned by work that we've been doing in these novel metastatic colon models, which was published in 2019, where we showed that CXCR2 biology again was controlling the metastasis of colorectal cells to liver in this KPM model. And actually, the advantages of these particular suite of colon models was that we could actually start to align these to disease. So we've sort of encouraged that this aligned to a sort of inflamed segment, and again that we were having this impact in the liver, although we didn't really have any impact on the disease progression in the colon, which is very similar to the results that we observed in the pancreatic models. So when we go back and consider the 5 Rs, we were sort of reasonably confident that we had data that supported the concept, at least, for progression for Everest in pancreatic liver mets, for prostate in combination with enzalutamide, which was the ACE trial. This is the papers from Andrea Ralamonti. And actually, the Everest trial was underpinned by the observation that we had for a role in colon metastasis. And then more recently, we also had developed a story that if you took fatty but not non-fatty hepatocellular carcinoma models, you would be able to again enhance checkpoint efficacy in liver-specific disease. So we felt that the platform of evidence that we had, that there was a potential, was there in the preclinical models. However, there were 2 major questions that we still don't really know the answer to. Well, we do, but we really haven't made progress on. So the major question we had is that when we looked at this at the retroscope, was that have we aligned the models to the right disease segment? So we know the colon models aligned to a particular disease segment. We didn't do a trial here, but we know what segment it was. However, if we look at the pancreatic data, we didn't really go into pancreas specifically in a segment that was reflective of the KPC model, and in particular of the genetics of the KPC model, bearing in mind that, for example, CDKN2A and other IO resistant genotypes are quite heavily dominant in pancreatic cancer. And then the second question we asked, particularly these early metastatic models, in reality, which is what they reflect, is really when we go into quite late stage second-line patients, did the clinical trial strategies that we had in combination with durvalumab were they really appropriate for the stage of disease where the preclinical models show efficacy? So we interpreted it in one way at a time, but when we look back, maybe there was further refinement that we need to do to our thinking. The second thing that we went back and looked at was our understanding of dose, the time of inhibition, and the frequency of inhibition. And we were pretty confident from work that we'd done in asthma and other models that we understood this left-hand side of the PK/PD relationship, because that's why we decided on 506 and our clinical candidate. However, when we went back and looked more carefully at the data with, again, with learning more about the biology, it was really clear that what we didn't really have was an understanding of the relationship between the degree of inhibition of targets, the inhibition of the impact of CXCR2 biology in the cell, and the outcome that I had, both in terms of tumor tissue and normal tissue biology. And I'll walk you through some of the evidence that we then we used to come to that conclusion. So one of the things that we did quite early on in development was take a dose that gave us a PK exposure that was very similar to the one that we felt that we would be achieving in humans. And we used CT26 tumors on the back of a skinned mouse just to do some pharmacology studies to understand the relationship between inhibition of CXCR2 and the reduction of neutrophils or PMMDSCs in the peripheral blood over time. And we found that in the peripheral blood that we could get a nice relationship between the exposure of 5069 shown in black and then the suppression of neutrophil activity in the peripheral blood And we could see that this PK/PD relationship justified twice daily dose and dose for twice a day, then we would get good cover, and we would get quite significant reduction in neutrophil levels in the peripheral blood, which were consistent with the known biology of CXCR2 controlling release into the peripheral blood. We then also looked in the tumour, again at 1 day and at 5 days, and what we found was that exposure at 1 day was not sufficient to modify, in the context of CT-TEC26 tumour, the level of neutrophils in the peripheral blood. But we did find that over 5 days, then you get into a point where you're starting to get, in the tumour, and at 5 days in the tumour, you started to get a drop in neutrophil content that was consistent with that we saw in the peripheral blood. So we saw a disconnect between the kinetics of tumour impact and over time versus the impact on the normal physiology. So we took this to suggest that we needed to get some durable cover over a period of time to ensure that we'd given sufficient modification of the tumour microenvironment to elicit a priming effect on the checkpoint inhibitor. This is just data from our head and neck trial scores, where we were also encouraged that at the 80 mg dose that we inherited from work that was done in COPD and asthma, that in cancer patients, we could again see these reductions in neutrophil counts in the peripheral blood. Now, unlike the preclinical models where the data is very tight, you can see from these plots that the modeling is very noisy actually when you go back and look at it. But you can still see that there is consistently a drop in the population. We were also given confidence that we were engaging target because in the right, you can see data from healthy volunteers where if we expose patients to the CXCR2 inhibitor, you can get an increase in IL-8 and CXCR1 that is again indicative of achieving good target engagement. And this is from a healthy volunteers study. And then this is the same type of study that was performed in patients with 40 and 80 mg doses of AZD5069, again in the head and neck trial, where we can see that we're increasing, again, biomarkers that we think are associated with having reasonable target engagement. So with that in mind, we then said, well, let's just go back and look at what the preclinical data tells us in terms of the behavior of the neutrophil biology in the KPC and the KPN models, the two metastatic models where we'd seen efficacy preclinically. And actually there, we then had a little bit of a surprise, because actually when we went back and looked at the peripheral blood suppression in the KPC model, and we had this data all along, but we hadn't really interpreted it in the right way at the time. What we saw in the KPN, in the KPC, the pancreatic model, was that at the metastatic stage, really CXCR2 wasn't having inhibition, was having no impact on the neutrophils in the peripheral blood. It was still impacting the tumour, and not fully. You can see that the residual neutrophils left behind in the tumour, when you look at day 8. Yeah, but it was not doing anything in the peripheral blood, which is very different from the CT26. If we looked at the KPN model, so the metastatic colon model, which was developed a few years later, in this model, the behavior is different. Here we can see that there is a 50% reduction in neutrophil levels in the peripheral blood. And again, we see a really big drop in the neutrophils that are present in the tumour. Again, this was measured by FACS, whereas this was measured by IC, so it's not necessarily comparable. But we can see that actually the biology of the inhibitor, that the target is different when we move between these two model states. And therefore calls into question perhaps whether it was appropriate for us to gain as much confidence as we had from the data that we had in scores, that we had the right types of exposure profiles with a given dose, and actually the ability to translate and migrate proof of concept between the different settings, because clearly this is sort of teaching us that biology in those models was changing. Okay. So we go back and look at this in terms of the reflections. What we can see if we look at the pancreatic trial that we performed, we did have strong preclinical evidence, and actually this is being built on by others. So Bob van der Heijden published a really nice paper, a very similar time to our 5069 paper, showing a role for CXCR2 in pancreatic cancer as well. But actually there were a few things that we would probably go back and do differently if we could, and it's probably important to think about for other trials with these type of inhibitors. This was a trial in second-line metastatic pancreatic cancer. Late-stage pancreatic patients were not really in a state where they would be able to be receiving multiple cycles of durvalumab. And secondly, perhaps in this setting, it's important that agents such as chemotherapy, just to give the tumor some control to allow that modification of the microenvironment and the enhancement of the immune system to work in the context of quite a challenging disease to treat. I think this is important to consider because quite a lot of us still continue to use the pancreatic setting to look at our myeloid cell biology. But when we think about translating it to clinic, it's really going to be very important that we get the right types of patients into the trial that reflect the stage of disease that we're really actually modeling in these preclinical KPC or KPC-line models. The second thing that we discussed a lot, because the precision panc team that was running Everest obviously was very heavy on genomic profiling, was the high prevalence of the CDKN2A and chromosome 9 aberrations that occur in pancreas. And we're in a position now where we're starting to look at those patients and maybe reflect that this is another indication that these patients, which dominated the Everest trial, may well have been intrinsically resistant to IO and actually did not truly reflect the biology that the KPC model was teaching us. So really the learning from that piece was that perhaps we need to go back and look a little bit more carefully at which subsets match the KPC model and then try and match into those patients and heavily select for that trial. The other learning was that we had, if we look back at the head and neck trial, was don't port a proof of concept from one disease to the next. So when we went into did the head and neck trial and scores, we didn't really have any strong preclinical data showing a role for neutrophil biology in head and neck cancer, and actually that data really hasn't evolved over time. And given the number of models that people may well have looked at for head and neck cancer, it may well be that neutrophil-like cells just don't play a suppressive role in this disease, and that actually that was perhaps not a great setting to test the concept that CXCR2 would combine with checkpoint inhibitor, and we got the result that you may not have expected. If we move to the right dose analysis, then the other thing that we considered was, well, did we have the right exposure? So at the time that we started with the AZD5069 trials, people were very concerned about neutropenia, and obviously CXCR2 controls neutrophil blood and neutrophil levels in the blood, as I showed you in some of the early clinical biomarker data in the presentation. So we were sort of cautious and really capped ourselves at 80 mg in humans, which was the dose at which they'd got significant reductions in COPD and asthma trials, but before a dose where it was predicted to give, what would be classified as a neutropenia like DLT. However, reflecting, it may well be that because this neutropenia that's induced with CXCR2 inhibitors is not symptomatic, it's not really associated with increased infection, and even within the COPD and asthma trials, there wasn't any observations of febrile neutropenia, etc. It could challenge ourselves to say, well, when we look at the degree of suppression that we get in the preclinical models and how that's associated with efficacy, is this 50% reduction, variable reduction in neutrophils, telling us that there's enough target cover in the cancer setting? Should a higher dose and more aggressive inhibition of CXCR2, even if it's not durable inhibition continuously, give us more chance of having effective outcome? And the second piece of data that we didn't understand in terms of the dose when we look back, because it's very challenging to get biopsies in these late stage diseases, is we still don't really understand the threshold of target inhibition that's required to get robust inhibition of these cells in the tumors. And actually, that's a really critical piece of information that if we had it now, we would be able to go back and recycle and design our trials more carefully. Now, QBIC is going to be a really interesting trial because it's got a very heavy translation element. And actually, within the context of that QBIC trial in HCC, between Newcastle and Glasgow, it's going to be quite exciting to see how they start to answer these questions with a whole array of on-treatment biopsies that they're going to derive from that trial. And then finally, I alluded to this in the earlier slides, the right combination. So in pancreatic cancer, it's challenging. Should it really be better to do a chemotherapy, myeloid cell depletion induction with a checkpoint inhibitor maintenance, in the context of a subset of pancreatic patients that don't have dominant features that would predict for bad outcome to immunotherapy. I'll come back to that later in the talk. If I can progress. So if we go back to this framework of just reducing it to a basic pharmacology problem, I think that, my learning in particular is that we don't really have enough of a handle on these relationships between the biological effects and the therapeutic index that we want to drive with these different drugs. And then why is that important? Well, if you start to sort of reduce it down to a noddy cartoon, one of the key things that we know from developing these molecules in many different settings is that it's all about balance and exposure versus normal tissue and tumor tissue effects to get the optimal outcomes. And here, what we're in the myeloid field, what we're trying to do is we're trying to look at what type of levels of neutrophil reduction or function inhibition or phenotype switching are we trying to achieve, or macrophage depletion or phenotype switching we're trying to achieve. Balance that with the off-mechanism effects that we would have because they play pivotal roles in normal tissues, and also the effects that those will have not as monotherapy, but when you bring forward them in the context of combination treatment, because obviously it's not just what the target cell type will do, but it's what it does when you combine it with other inhibitors. So for CXCR2, we may have the ability to reduce neutrophils to a given level, and that's fine. But if you look at the disease axis, it may well be that to get the desired effect, even in combination, that the threshold of cell depletion that we need to get is going to be higher, even in settings where we believe that there's a good case for activity in a preclinical model that would predict that there's a value for human disease. It's possible that there's neutrophil controlled tumors where in the right combination setting that the threshold is lower, and that perhaps a smaller reduction or a reduction that's equivalent to this 50% reduction that we go with is sufficient to drive efficacy. But we've not been able to identify that setting yet. And of course, obviously, there are many diseases like the head and neck setting where it doesn't matter how hard potentially you hit this axis, you're going to get no anti-tumor benefit. And then the second is, well, actually, is a neutropenic-like phenotype actually the true biomarker that you want to aim for in terms of the degree of target inhibition you want to get with this type of target? If we switch the same principle to the macrophage targeting drugs, we're really clear. We do have a very clear outcome where CSF1 inhibitors in particular in TGCT do have monotherapy activity, and the degree of compound exposure that we need to have to get that and sustain activity is perhaps lower than the concentrations at which you need to achieve to get some of the normal tissue effects that may limit the exposure of these inhibitors. If you go higher, do you get more chance of infection? But if you go higher, do you inhibit more of the biology that's required to prime the efficacy in combination with these different diseases? This is a question that's still ongoing. There's some really nice studies, one from the Roche group, that's shown a lot of preclinical data looking at the relationship between target inhibition with CSF1 inhibitors in different diseases. Again, that will be very important for us to learn more as we develop these drugs. Pharmacology is not the only answer. I feel, even despite the fact that we're now starting to get well-annotated data sets, that with outcome data, with lots of good peripheral blood samples and tumor biopsies, with checkpoint inhibitors in particular, that it's not really very clear where the neutrophil of the macrophage biology is dominant within the context of all of these different features that are described broadly to influence the outcome to checkpoint inhibitors or even the outcome to chemotherapeutic drugs. I think finding which diseases are more dependent on the myeloid cells and in which subset of that disease is going to be really critical for these really exciting therapies that are being developed. And enriching for those segments in these early stage clinical trials is critical. Again, I think going into late stage pancreatic is perhaps not the best thing to be doing. Are there more innovative trial designs that working with different groups that we can develop, where we're going into earlier disease, maybe patients who are high risk metastasis, which are perhaps more reflective of the situations where we did the preclinical modeling. There is biomarker data starting to emerge, as I alluded to. These are really two very interesting papers that got us quite excited a few years ago around ILA that may point to a disease segment and a biomarker that could be used to select CXCR2 inhibitors. But more broadly, I think it's important that we start to develop our preclinical biology to look at it in the round, so that we look at this, not just the myeloid cell biology, but actually the myeloid cell biology in the context of our optimal T cell response and in the context of targeting the tumor cell. That then leads into a natural transition into this concept, which is that at the moment what we do is we give long-term durable inhibition at a tolerated dose, or a perceived tolerated dose of the myeloid therapy, and we may add on chemo or a checkpoint inhibitor. But actually, can we be bolder and start to compare dose and schedules for these inhibitors to really do what we think they're doing in the preclinical models, which is remodeling the tumor microenvironment to prime them to be receptive to intervention with chemo or checkpoint inhibitors, and then allow the normal immune system to recover, and then repeat the cycle as we go through rounds of repriming of the microenvironment. These are the sorts of things that may be important for us to think about as we move forward with a new generation of drugs, or even perhaps consider revisiting ones that we've already tried. I feel as though when we went into this, we didn't really have a handle on what success would look like. This is what we dreamed of, this curve, where we saw this massive uplift in an unselected patient population because myeloid cells were the key resistance feature for chemo or for checkpoint inhibitors. It's now clear that monotherapy efficacy is unlikely in the majority of solid tumor settings with these drugs, but we're still not clear whether overall response rate will be improved or whether it's duration of response that we really need to look at, and what uplift in efficacy over control would be expected if we're not in a selected patient population, and can we spot that efficacy. The power of the study becomes really important when we do this. A lot of our phase 1s and phase 2s, if you analyze them, have been 20 to 30 patients. They're not controlled phase 2s. So we've only, 20% of them are going to respond to a checkpoint inhibitor, and 5 more are going to be beneficial when you add the myeloid therapy on top. Is that going to be sufficient signal to encourage other people to invest further into late stage controlled phase 2s or even phase 3 trials when there's lots of other competing exciting therapies around to trial in different settings? I think that's probably an important consideration as we move forward. However, there is really exciting data that's starting to emerge. Obviously, eglolisib, which is starting to show and report in their investors' briefings really nice data here in an unselected trial in bladder cancer, second-line bladder cancer. They've reported that in a 2-to-1 randomized trial, they've seen a big uplift in overall survival benefit in combination with checkpoint inhibitors with eglolisib. And this is building on obviously Judith's work that was published a number of years ago. They also have potential signals in combination with chemotherapy and checkpoint inhibitors in TNBC ovarian cancer trials, as well as in head and neck and squamous cell melanoma trials. There's some really exciting studies being done by BMS, where they're looking at CXCR2 and IL-8 antagonists, comparing macrophage and neutrophil modulating agents in parallel in different diseases, and that will give some really interesting data, particularly if they have a heavy element of biomarker investigation associated with them. And in addition to the activity seen in TGCT, there's also been a recent study that Carola Rees pointed out to me by email, which was an activity of another CSF1 inhibitor in controlling graft-versus-host disease, which is a major driver of resistance to CAR-T and immunology intervention in hematological disease. So we're making progress clinically, but I think that there's still work to do, despite the fact we've got exciting signals. There's a lot of agents that we're looking at. There's a lot of future opportunity to target myeloid cells and build on the learning that we've had with these first agents. I think there will be positive benefits seen soon. There's a learning from eganolisib suggests that reprogramming the cells is the most effective way forward, and that depletion or inhibiting migration is perhaps less effective in a broader population. And then the two critical questions that I'll leave you with is, where are the new myeloid agents that we're developing going to be positioned? What's the disease and the disease segment that we want to use them in? Rather than go into an unselected 20 patient or 30 patient trial in phase 2, can we be more clever and smarter about using the existing translational data to do it more effectively? And then coming back from the other direction, there are a whole host of studies now starting to find myeloid targets such as TREM2 from disease profiling in specific diseases. Will these translate into being much more effective agents in specific disease settings? And is that the way to go in terms of targeting myeloid cells and in harnessing this clear association that they have with resisting both chemo and checkpoint inhibitor treatment? Thank you. Thanks for listening. Last slide is the talks, and these are the various people who've been involved in a lot of the work that we've done to underpin our understanding of development of these agents.
Thank you, Simon. Thank you very much. We have a lot of questions, big interest. So what I will try to do to stay on time, I will read them in a little bit abbreviated form and without name, and just people forgive me about that. And I ask you to try to answer to the point, right, without long, because the questions are very interesting and probably will require another hour to talk about them. So the first question, with our understanding of neutrophil heterogeneity in tumor models, do you know if persistence of circulating granulocyte with the CXCR2 inhibition in KPC model, for instance, result in selection emergence of alternative fate trajectory? Basically, are this emergent population suppressive in T-cell assay? So you basically select one against another.
Yeah, that's a good question. We don't know. That's work that needs to be done. And actually, it's even work that could be done from human disease, because we do see this bifurcation of controlled and non-controlled peripheral blood neutrophils in human disease.
So second question is about changes in fibroblast in KPC models upon treatment.
Yeah.
Do you have any data on that?
Yeah, so that's in the Steele paper. So one of the really key things that we've seen in the KPC model in particular is the thinning of the stroma, both with CSF1R inhibitors and with CXCR2.
Third one, do you see blocking neutrophils affect T-cell infiltration because of in multiple models? Because
yes.
myeloid cells go hand to hand, it's just a question.
Yes, so CXCR2 will allow to some extent T cells back into the KPC model, even though it shows no efficacy. CSF1R in the primary KPC is really efficacious, but CXCR2 will do some tweaking, but maybe the threshold is too low.
Mm-hmm. So another question, try to ask you to clarify some of your early statement, because in the beginning of your timeline, you mentioned CXCR2 dependent neutrophils, quote unquote. Do some neutrophils express only CXCR1 or CXCR2? Are they always express only, are they related to their function? So basically, to clarify what the CXCR2 positive neutrophils are.
So that's a difficult question. I don't know if there are CXCR1 only expressing neutrophils. I'd have to go back and check for that answer. The reason why we express it as CXCR2 expressing is that we early on is that we define that by using genetic knockouts in mice, and we did some work with the group at Sheffield where we saw that CXCR2 would control certain neutrophil populations, but there was some CXCR2 independent recruitment to tumors in early systems. That I think we published that in 2006.
Okay, so this actually answered the second next question, so I will skip that. So another question, targeting one myeloid cell type often results in an increase in the other myeloid cell types. Can you comment on combination therapies that address this problem?
Yeah, so I mean, obviously, Dimitri published one of those papers. that's really
It wasn't
interesting.
my question. It's not from me.
He's loading the dice. So we're doing some work, well, the role in the collaboration we have with the Beats, and we're doing some work to address that question, to look at residual populations with different treatments. The concern with the combination of neutrophil and macrophages, can you get to a high enough suppression? Do you need a high macrophage control and a low neutrophil control, or vice versa? Because if you go and do both of them to the degree that you need to probably do both of them too, will you get a lot of opportunistic infection? So it's just that risk of infection, that has been the thing that's been a big debate for us in project teams.
Good. So next question will basically ask the same one, so we skip it. You answered, and it looks like the last one, unless anyone just rushed to type something, the last question will be the second. The curiosity is regarding your graph where you show the blood granulocyte / tumor neutrophils ratio. Comment really nice. Maybe I missed it, but how did you differentiate this population? And do you take into consideration also eosinophils and basophils inside the blood granulocyte population?
So in the human data,
I cannot say. I read it,
so
the question.
We separate out basophils, so it's purely neutrophil populations that are in those CXCR2 control. We haven't looked at other subsets of cells that are controlled by CXCR2 in the peripheral blood. So it's a good point. There may be other things going on.
Well, I think we made fantastic job with you, Simon. We stay on time and addressed all the questions asked. Thank you very much again. And I will give it floor to Judy.
Thank you.
Thank you very
Simon.
Great talk. Actually, Joanna is going to take over, and I'm just...
Joanna. Okay, sorry, I missed that point. Who is taking over?
No problem. So thanks for giving me the session that's aligned with the late afternoon here in Europe. And the first speaker of the short talks will be Rongje, I hope I pronounced your name correctly, Olivia Liu, who's an assistant professor at UCSF. And she will be speaking about STING interferon signaling in tumor-associated macrophages.
Thank you so much for the introduction. Actually, Dr. Joanna Joyce, I have followed your work for many years and used your data set on your publicly available. So today I'm going to talk about the role of PP2A and STING in the STING type of interferon signaling pathway in TAMs. My lab has been focused on this serine and threonine protein phosphatase 2A, and in the past we have identified targeting the catalytic subunit of PP2A using a small molecule inhibitor can sensitize the tumor to radiation in PD-1 blockade and chemotherapy. However, the mechanism is really not very clear because PP2A is widely expressed in multiple types of cells. And second, PP2A is actually a hormone enzyme. The B regulatory subunit is very heterogeneous, so that it can have different combination because of different B regulatory subunit to lead to 60 or 100 different types of combination. And therefore, it's very important to decide the B regulatory subunit, which decide the specificity and the substrate downstream signaling pathway. So this is one of my research goals, is to identify the specific PP2A complex in the major cell types in the tumor microenvironment, so that we can develop more precise approaches to target the PP2A. So while we are interested in PP2A in macrophages, this is stemmed from a paper on immunity. They found that in infectious models, upon toll-like receptor stimulation, PP2A deficient macrophages have enhanced the type of interferon production. And then we know TAPA interferon from the myeloid cells is very important to elicit the anti-tumor immunity. And in tumor microenvironment, the STING TAPA interferon is more relevant, but whether PP2A regulates STING TAPA interferon in tumor is unknown. So we're very fortunate to obtain this LINS-M Cray PP2A flopped mice from Dr. Moore's lab and Michigan. And we use BMDM cells, and we stimulate with STING agonist. And indeed, we found that the TAPA interferon signature is highly enriched in the PP2A knockout macrophages. And whether this is can affect the tumor growth, and we did multiple tumor models, including the glioma model on SP28. We also did both subcu and intracranial injection. And we found that the tumor growth and all mice survival was improved in this knockout mice. And then we further did the single cell RNA-seq analysis of the immune cell population, and we identify those those are for the TAMS clusters, and we identify actually the most dramatic change between the PP2A knockout mice versus wild-type mice is this macrophage TAPA interferon cluster. This is further corroborate with our in vitro BMDM data stimulated with the CGAP. And then we're wondering whether this TAPA interferon signaling pathway is responsible for the phenotype in vivo, and we're blocking the TAPA interferon signaling by the antibody, and then we found that it abolished the reduced tumor growth in the PP2A knockout mice. And further, we make this CGAS knockout 9, which they could not produce any CGAP, and then the CGAP cannot be transported out from the tumor cell to activate the TAMS. So this this allow us to study whether the phenotype in vivo is from the CGAS STING signaling pathway. And once they inject those CGAS knockout mice to the PP2A host knockout mice, we do not see any difference. It suggests the phenotype we saw in terms of tumor growth in the PP2A knockout mice is dependent on the CGAS STING TAPA interferon signaling pathway. So next, it's more interesting. We want to identify the signaling mechanisms, and we through the siRNA screening of all the B regulatory subunit, we identify the stratum-4 is a regulatory subunit to partner with the catalytic subunit or PP2A to regulate STING TAPA interferon. We further verified that with using the stratum-4 CRISPR knockout macrophages. And what is stratum-4 and what is the downstream signaling pathway? So stratum-4 previously formed by chemical work or in tumor cells, they found that stratum-4 can partner with PP2AC and to regulate the Hippo pathway, MST1. But whether this is relevant in macrophages or tumor-associated macrophages is totally unknown. So we tested in macrophage to indeed the knockout stratum-4 in macrophages enhance the STING TAPA interferon signaling pathway, and meanwhile enhance the Hippo kinase MST or the substrate PMOB signaling pathway. So what is the role of Hippo kinase in STING TAPA interferon, whether those two pathways interact with each other, then we further test this, use this MST1 and 2 inhibitor. And we found that by treating with the macrophage with this Hippo kinase inhibitor, it totally abolishes the STING activation in both wild type and the PP2A knockout macrophages. This suggests this Hippo kinase MST1 is essential for STING activation, and also PP2A regulates STING TAPA interferon through this Hippo kinase. So how Hippo kinase regulates STING TAPA interferon? And the most classic role of Hippo downstream is this YAP10 signaling pathway. So HIPO will induce phosphorylation of YAP-TAZ, and YAP-TAZ will go to degradation. YAP-TAZ is a well-studied transcriptional factor for tumorigenesis and for organ development. However, the role of YAP-TAZ in tumor macrophages is not very clear. And previously, the two papers also in antiviral model, they found this non-transcriptional activity of YAP-TAZ combined with TPK to inhibit the type interferon signaling pathway. So whether this is YAP-TAZ can inhibit STING type interferon in TAMS, we would like to is unknown. So first we test this. We use both a wild type and this YAP or non-transcriptional activity of YAP. We overexpress it in macrophages. We found it indeed suppress the type interferon signaling pathway. And whether this is relevant to the tumor environment, actually we use the public available data set from Dr. Joyce's group, and this is compared with the monocyte-derived microglia from the GBM patient compared to the non-tumor control patient, and the YAP signature is highly enriched in the TAMS. More interestingly, this is the non-transcription activity of the YAP signature also is enriched in the TAMS. And we also did in our in vitro model, just treat the macrophage with tumor condition medium can enhance the YAP production. But in PB2A, this YAP enhancement expression is suppressed. And this accordingly with this response to STING activation. Once we treat with tumor condition medium, then they just do not respond to CGAP very well, but this can be reversed when we knock out PB2A in the TAMS. So how this HIPO and YAP and PB2A regulate them, and further we did this, whether the HIPO kinase is true the downstream substrate of this PB2A stratum 4. We did the co-immunoprecipitation, and we found that in the resting phase, the PB2A associated with MST1 and 2 very tightly, but upon the CGAP stimulation, they just start to dissociate, so that the MST1, 2, and HIPO kinase can be released to induce the YAP-TAZ degradation. However, in the tumor conditioned environment, no matter you treat with or without CGAP, the PB2AC, PB2A, and HIPO kinase always associate with each other. And this interaction is mediated by this B regulatory stratum 4, because in stratum 4 knockout macrophage, this in PB2A do not interact with HIPO, MST1, 2. So this is summary. We found that by YAP-TAZ gene signature is highly enriched in TAMS, resulting in reduced response to STING agonist, and by targeting either PB2A catalytic subunit or B regulatory subunit stratum 4 can enhance the STING type interferon signaling pathway by induce the YAP-TAZ degradation through the HIPO kinase pathway. So I would like to thank my collaborator and my lab members, two really outstanding students who have the passion for physician scientist career path. And also I just become a new mom. This is my baby, 5-month baby. So thank you.
Thanks very much, Rongjae. Congratulations for both your new baby and also your new paper. Maybe I start with a quick question. I think we have time for maybe 2 quick questions. What I'd like to ask you is, in the data you showed at the very beginning, you mentioned that you looked at GBM or glioma cell line subcutaneously as well as intracranial, and I think it was in the PP2A knockout context.
Yeah.
And I wondered, did you see any difference there? Because you probably know this study that was published in Cancer Cell quite recently from a group at Duke University, where they found differences in terms of STING activity in the brain at baseline. So maybe you can comment on that quickly. That would be great.
Yeah, so that paper from the Duke, they really focus on the STING signaling pathway in the tumor cells. And the methylation profile affect the STING response. So my model is really focused on the myeloid cell, mainly the macrophages. We also see the neutrophils affect because of NISAMCRE. And so actually from many years ago, Dr. Hideo Okada's lab at UCSF, they found that STING signaling from in the brain tumor microenvironment actually mainly from the myeloid compartment, not from the tumor. The tumor minimally make type interferon. So that's why we focus on the TAMs. And yes, we did the intracranial model, and so sub-Q model is more responsive. Without any treatment, we can see the tumor growth reduced, but in intracranial model, it's always more immunosuppressive because the microglia population is also there, and we do not see any difference between the wild type and PB2A alone. But with radiation, we see significantly improved of overall survival. There's multiple explanation for that. One is that maybe the STING activation needs a boost through the radiation. And second, maybe the microglia, because the NISAMCRE is not efficient for microglia population. So the microglia still can have immunosuppressive function in the intracranial model.
Right. Yes. Yeah. That would definitely be consistent with what we and many others have seen. Wow. There's 4 questions that have popped up here in the chat.
I can answer if I run out of time. I can answer offline. I'm happy to answer.
Exactly. So I'm just going to randomly pick one of those, and I'm going to pick one from our great co-organizer Judy Bonner. Great talk. What are the various stimuli that can activate PP2A that might be in the tumor?
Yeah, we have another manuscript on the revision cancer research. Yes, so the radiation definitely can activate the STING PP2A path in the tumor cells. And also in the tumor, the PP2A may also regulate the CGAS STING pathway. You mean in the tumor cell? Yeah.
Yeah. Okay. Wonderful. Thanks very much again. If you are able to answer the questions in the chat, that would be wonderful. Thank you, Rongjay. And the next speaker, there she is Maria Caffarel. She is at the Ikerbasca Biodonista Health Research Institute, which is in beautiful San Sebastian in Spain. And Maria will be speaking about perhaps some recently published work. From the title, it looks like it might be your recent paper on the important roles of oncostatin M and immune suppression. So Maria, we're looking forward to hear from you. Thank you. There is another Helen McRae. I guess she's a postdoc at the Salk Institute. And Helen will be speaking about epigenetic reprogramming of tumor-associated macrophages. Thanks, Helen.
Thanks so much, and thanks for the opportunity to present today. It's a real honor to present in front of this audience. And the work I'm going to be talking about today is currently unpublished, so I really appreciate any suggestions or feedback that you have. So a big question in the field of immune oncology is how can we convert immune cold tumors that contain more immunosuppressive cell types and are associated with poor prognosis to immune hot tumors that contain more cytotoxic cell types and are associated with better response to checkpoint blockade immunotherapies. And one method that's promising that we have to achieve this is through reprogramming tumor macrophages. So I won't spend much time on the introduction here, given the audience we have today. But basically, the aim is really just to boost the anti-tumor properties of tumor-associated macrophages. And there's been a lot of work done to understand the cell surface receptors and signaling pathways involved in tumor macrophages, but comparatively less is known about what's going on inside the nucleus of tumor macrophages. And so I'm really interested to contribute here to this question of what transcription factors and epigenetic regulators are involved in regulating tumor-associated macrophages. In the Hargreaves lab, we're particularly interested in the BAF or switch-SNF nucleosome remodeling complex. So this is a large multi-subunit complex whose canonical function is to regulate gene expression through nucleosome remodeling. And the BAF complex is the target of ongoing pharmacological research into the development of inhibitors and degraders, given that there are certain cancers that depend on BAF complex subunits for their survival. So of course, these inhibitors and degraders can directly target tumor cells, but they also have the potential to affect cells of the tumor microenvironment. So I'm particularly interested to understand the role of the BAF complex in tumor-associated macrophages. And what I'm going to talk about today is work focused on the largest subunit of the canonical BAF complex, ARID1A. So the question that I asked is, if we delete ARID1A in tumor macrophages, how does this affect the balance between pro and anti-tumor properties? To address this question, I used a genetic mouse model with a floxed ARID1A allele and the lysem-cre knock-in gene, and injected these mice subcutaneously with the MC38 cell line. You can see here that compared to controls, mice lacking ARID1A in their myeloid cells had on average slower tumor growth. So this suggests that by deleting ARID1A in myeloid cells, we can increase the anti-tumor properties of these cells. To get some insight into the mechanism here, I performed RNA sequencing on cells or tumor-associated macrophages sorted from this model. You can see here there were several up and down regulated pathways, including upregulation of the inflammatory response pathway and also the interferon alpha and interferon gamma response pathways, shown here as barcode plots. So these data sets contain largely overlapping sets of genes, and the union of those that were upregulated in the ARID1A knockout TAMs are shown here. What stood out to us among this list was these genes encoding these two really important cell surface receptors on macrophages. So CD86, which is involved in co-stimulation of T cells after antigen presentation, and CD274, which encodes the immunosuppressive PD-L1. So this is an immunosuppressive protein, but it is upregulated in response to inflammation. So I've shown that tumors lacking ARID1A in their myeloid cells grow slower, and we have upregulation of ISGs, including PD-L1 and CD86. So for the rest of the talk, I'll talk firstly about some mechanistic questions, investigating how does ARID1A actually regulate PD-L1 and CD86. So given that these are ISGs, they are stimulated by interferon, but also regulated by several other cytokines, we considered the possibility that the upregulation of these in the ARID1A knockout TAMs might be a secondary effect caused by altered cytokine production. We also considered the possibility that ARID1A might be directly regulating these loci. So I'll talk about these mechanistic questions first, and then I'll talk about some functional data addressing this question of can we actually boost response to anti-PD-L1 immunotherapy by deleting ARID1A. So to address the mechanistic questions, we turned to an in vitro system of bone marrow-derived macrophages, and using flow cytometry staining for CD86 and PD-L1, you can see these histograms here of either unstimulated or low-dose interferon gamma stimulated cells. And in each case, looking at the quantification here, we saw that both CD86 and PD-L1 were upregulated in the ARID1A knockout macrophages, recapitulating what we saw at the RNA level in the tumor-associated macrophages. So then to ask whether ARID1A is regulating these molecules in a cell intrinsic or cell extrinsic mechanism, we turn to a co-culture system. And here we can distinguish cells based on the CD45 receptor, either CD45.2 or CD45.1 for the co-cultured cells. And just to give you an example of the expected results for PD-L1, so we expect in the wild-type co-culture, these cells should have comparable basal levels of PD-L1. We expect that ARID1A knockout cells, which are CD45.2 positive, will have upregulation of PD-L1, as we saw previously. And then the two hypotheses we considered is that if ARID1A is regulating these molecules in a purely cell intrinsic manner, we'll expect this upregulation only to be present in the ARID1A knockout cells and not in co-cultured neighboring cells. On the other hand, if ARID1A knockout cells are producing abnormal cytokines that are going out and then regulating CD86 and PD-L1 through a paracrine mechanism, we'll expect these same factors to also signal to neighboring cells. So we'll expect upregulation there. And looking at the results here, you can see that in the control co-culture, as expected, we see basal levels of PD-L1. We see upregulation in the ARID1A knockout bone marrow-derived macrophages, and then in the neighboring co-cultured cells, we see basal PD-L1 expression again. So this suggests that this first hypothesis of that in the ARID1A knockout cells, we're experiencing upregulation of PD-L1 in a cell intrinsic manner. And this, I'm just showing you one result here given time constraints, but we saw similar results with CD86 and also in the interferon gamma stimulated cells. So this led to the hypothesis that ARID1A might be directly regulating these genes. And indeed, when we look at ARID1A chip sequencing tracks to see where it's bound at the genome, we see that ARID1A is bound at the promoters of CD274, which encodes PDL1, as well as CD86. And then looking at attack sequencing, which measures chromatin accessibility, we see that there is increased accessibility at the promoter of both CD274 and CD86 in ARID1A knockout tumor-associated macrophages, suggesting ARID1A might be directly repressing these genes. So finally, I'll talk about whether we can boost response to anti-PD-L1 immunotherapy. And so I'm sure most of you are aware that anti-PD-L1 blocking antibodies will block the immunosuppressive interaction between PD-1 on T cells and PD-L1 on tumor cells. And also that, at least in preclinical models, it's been shown that PD-L1 expression on antigen-presenting cells like macrophages and dendritic cells is also blocking this PD-L1 is really important for the efficacy of anti-PD-L1 therapy. So to see whether PD-L1 was actually upregulated at protein level on ARID1A knockout tumor macrophages, I performed flow cytometry, and you can see here that we see an increase. So then the question was, can we boost response to anti-PD-L1 therapy? So we treated these mice starting day 13 once tumors were already established every 3 days with anti-PD-L1. And you can see here that in the isotype treated mice, we see similar to what we saw in the untreated situation, where mice lacking ARID1A in their myeloid cells will grow on average slower. And then as we expect for the partially responsive MC38 model, we see that anti-PD-L1 treatment will slow tumor growth, but we see the most robust response in mice lacking ARID1A in their myeloid cells that are treated with anti-PD-L1. So this suggests that the efficacy of anti-PD-L1 therapy has been increased when we delete ARID1A in myeloid cells. To get some insight into the cellular mechanism here, I performed flow cytometry on the immune infiltrate. And you can see here staining for tumor-associated macrophages using this gating strategy. We had a reduction in the proportion of tumor macrophages among the immune infiltrate when ARID1A was deleted, regardless of treatment. Then on those macrophages that were present, we saw an upregulation of CD86, in particular when mice lacking ARID1A were treated with anti-PD-L1. And we also saw upregulation of MHC class 2 and a downregulation of CD206 on all 3 conditions compared to the isotype control. And representative histograms are shown here. So we've seen that deleting ARID1A can affect expression in macrophages, but we also wondered, is this changing other components of the immune microenvironment? So I stained for lymphocyte markers, and you can see here that both CD4 and CD8 T cells were increased as a proportion of the immune infiltrate in mice lacking ARID1A in myeloid cells that were treated with anti-PD-L1. So to summarize, we've shown that if we delete ARID1A genetically in myeloid cells, we create a more permissive tumor microenvironment immunotherapy. These ARID1A knockout tumor macrophages have upregulation of inflammatory and interferon-stimulated gene signatures, including upregulation of the important molecules PD-L1 and CD86. And I've shown that these were increased in a cell intrinsic mechanism, and that ARID1A is bound at the promoters of both CD274 and CD86, and there's increased accessibility at these loci in tumor macrophages. If we combine this with anti-PD-L1 therapy, we see improved response and also changes to the immune infiltrate. So I just wanted to acknowledge my supervisor, Diana Hargreaves, Catherine Nguyen, a master's student who recently finished her thesis and contributed to work on this project, including some of the in vitro data I showed today, and as well as Jingwen Liao, a PhD student in the lab who performed the chip sequencing experiment that I showed here. Thanks.
Thanks very much, Helen. That was a very interesting biology that you uncovered there. I have a question, maybe to kick things off. Thinking about the how to translate results like this therapeutically, right? Because you see this effect in this genetic model is very interesting, but how can one then translate that? So did you do an experiment, for example, adoptive transfer of ADAR1 deficient monocytes to see if they can transfer that phenotype into recipient animals?
No, but I think that is a good experiment to do to really see if there's kind of a gain of function phenotype there. Yeah, I think that will be really interesting. I haven't done that yet.
Okay, so I'm going to read off some of the questions here. I'm sorry if the question, sorry, they're bouncing around. I'm sorry if I missed it. Is this interaction between ARID1A and PD-L1, like the upregulation of PD-L1, only happening in TAMs or also in tumor cells?
So I used a kind of, I didn't have a marker to gate specifically on tumor cells, but if I gate on CD45 negative cells kind of as a proxy for that, I don't see upregulation of PD-L1. So I think it is very specific to the tumor macrophages.
Another question, again, kind of coming back to the therapeutic implications of your results. ARID1A is also a tumor suppressor in some cancer types. Would you worry about targeting ARID1A in the future?
Yeah, I think it's a really good point. Of course, there's definitely potential for kind of toxic effects, both given the tumor suppressive roles of ARID1A, but also just given its importance in normal tissues as well. So I think the key to translating would really be identifying, therapeutic window or delivery mechanism where you can really specifically just target the tumor and also maybe using, as you suggested, kind of an adoptive transfer approach, or, maybe upregulating the potential of CAR macrophages, for example. So I think, but it's definitely something to be considered. Yeah, no,
it's very challenging with regards to the different cell types, particularly if they have opposing functions. So the last question that I'm going to ask then, Helen, is from Judy. Where's that question gone? Okay, is BAF required for cell survival? Are there other genes that can replace ARID1A in the context of the genetic deletion that you did?
So is BAF required for cell survival? I think in macrophages, it doesn't seem to be. When we generate bone marrow derived macrophages, they are totally deleted for ARID1A. And we see that although we are seeing less, proportionally less tumor macrophages, we actually see that it is really well deleted. So we're not just getting a loss because we're losing those cells that get deleted. And what was the second part of the question?
Are there other genes that can compensate for ARID1A?
So there is ARID1B, which is another factor that's kind of mutually exclusive with ARID1A in the canonical BAF complex. So it's possible we do see some effects that we might see, an increased effect if we also deleted ARID1B. I think if that's what the question's asking.
I think so. But again, check it out in the chat. There's a few other questions that have popped up in between answers to other people's questions. So thanks very much again, Helen. And the last speaker for this session of short talks is Michelle Williams. And you can read where she is from. She's from the University of Colorado, and she will be speaking about heme metabolism and macrophage immune suppression. Also looking forward to this. So Michelle, thanks very much.
Sorry about that. My mouse is deciding not to work all of a sudden, so I had trouble unmuting myself. But yeah, I'm really excited to share with you guys today my work that's looking at the impact of breast tumor cell heme metabolism on the macrophage microenvironment in lung metastasis. And I apologize for my mouse being really crazy. Let me see if I can hide. Okay. So before getting started today, I just want to take a little bit of time at the beginning of this short talk to thank the members of the Ricker Lab, as well as collaborators and summer students and rotation students and core facilities at the University of Colorado who have been really essential for the development of this project. I'd also like to thank funding sources and the organizers of this wonderful symposium for allowing me to share this story with you today. So the overall goal of my postdoctoral project was to identify additional immune modulatory pathways that are upregulated in triple-negative breast cancers during metastasis. In order to do this, our group and others have manipulated an oncogenic epithelial to mesenchymal transition, or EMT program, in triple-negative breast cancers because this is a pro-tumor pathway that's often co-opted by triple-negative breast cancer. So in the Ricker Lab, we do this by taking mesenchymal-like triple-negative breast cancer models and reverting them to a more epithelial phenotype using the powerful repressor of EMT, the microRNA miR200C. We can then compare cells that are in this more epithelial state to more mesenchymal-like state to identify pathways that are upregulated in TMBC. And a number of these pathways that we've identified are actually immune modulatory, and they are further upregulated during metastasis. I became interested in further following up on some of these pathways that might be targeted with FDA-approved therapies that might be approved for use in other diseases and could be repurposed for use in triple-negative breast cancer, as well as those that impact the microenvironment through secreted factors. So this led me to a particular interest in metabolic pathways that we identified with this approach that may alter the microenvironment through their secreted metabolites. Today, I'll tell you about heme metabolism, where heme is broken down by heme oxygenase 1 into 3 different immune modulatory byproducts. I'll focus on biliverdin that's quickly converted by biliverdin reductase into bilirubin. I became interested in the impact of bilirubin on the tumor microenvironment because it's been shown in other diseases like autoimmune disease and in models of organ transplant to have a profound impact on a number of immune cell subtypes, including T cells, and it can suppress the function of myeloid cells, including phagocytosis and antigen presentation, by decreasing expression of cell surface receptors that are required for these processes. This suggests that bilirubin could have a dynamic impact on the tumor microenvironment, but it had never been studied as an immune modulator in cancers. So to begin understanding whether or not tumor cell heme oxygenase 1 might modulate the microenvironment in triple-negative breast cancers, I did data mining of publicly available data sets using CyberSort to predict the relative immune cell abundance of immune cells in triple-negative breast cancer specimens from the Cancer Genome Atlas. Here I stratified patients on the x-axis by expression of HO1 at the mRNA level, or HMOX1, and saw that high levels of HO1 predicted a slight but significant increase in CD8 positive T cells, but no change in T regulatory cells. However, the immune cell subtype where we saw the most dynamic change was a predicted increase in the number of M2 pro-tumor macrophages, suggesting that the microenvironment of HO1 positive tumors might be slightly warmer because there are more CD8 positive T cells, but ultimately this might be suppressed by the macrophage population. So I hypothesized that triple-negative breast cancers upregulate heme metabolism during metastasis in order to support a pro-tumor immune microenvironment. In particular, I was interested in the impact of bilirubin on macrophages and whether we could suppress this process by inhibiting tumor cell heme oxygenase 1 using genetic approaches like shRNA or pharmacologic approaches like the HO1 inhibitor tinmesoporphyrin, or SNMP, that's approved for use by the FDA in severe cases of jaundice. To begin understanding whether tumor cell heme oxygenase 1 impacts macrophages, I cultured 6,6-CL4 mammary carcinoma cells that express a moderate level of heme oxygenase 1 and treated them either with DMSO control or the HO1 inhibitor tinmesoporphyrin to decrease enzymatic activity of heme oxygenase 1 and bilirubin secretion. I then took conditioned medium from these cells and placed it onto raw 264.7 mouse macrophage cell line and looked at a number of different immune suppressive and functional genes using QRT-PCR. Culturing macrophages with HO1 inhibited conditioned medium in blue led to a significant decrease in the immune suppressive genes arginase 1 and TGF-beta 1, but an increase in the functional gene MERTK, which is a receptor tyrosine kinase involved in efferocytosis or engulfment of dead cells. However, when I restored bilirubin levels in this conditioned medium treating with 2.5 micromolar exogenous bilirubin, gene expression was rescued, suggesting that tumor cell heme oxygenase 1 could dynamically impact the microenvironment through its secreted metabolite bilirubin. At this point, I became really interested in the impacts of bilirubin on macrophages and turned to a number of different macrophage models, including what I'll show you today, which is primary bone marrow-derived mouse macrophages. I isolated and differentiated these cells and then treated them with an increasing concentration of bilirubin and looked at a number of immune suppressive factors, including PD-L1. Treatment with bilirubin increased expression of PD-L1 on bone marrow-derived macrophages at the mRNA level. I thus conducted a similar experiment and isolated and differentiated bone marrow macrophages, but then alternatively activated them by treating with IL-4 and 13, and then looked at PD-L1 expression using flow cytometry. Here you're looking at bone marrow-derived macrophages that were isolated from 3 different donor mice. And while we see quite a lot of PD-L1 expression in these macrophages with just IL-4 and 13 treatment, we see an almost significant increase in PD-L1 with the addition of bilirubin, suggesting that in the tumor microenvironment, where there are a number of signals that might enhance the immune suppressive properties of macrophages, bilirubin could potentially be additive or synergistic with these signals and create a macrophage population that's particularly immune suppressive. Thus, I'm currently optimizing assays to understand whether or not these bilirubin-induced macrophages can functionally suppress the activity of cytotoxic CD8 positive T cells. Another function of macrophages that I'm interested in is efferocytosis. So to begin understanding whether or not bilirubin might impact efferocytosis, I looked at mRNA expression of two of the receptors that are involved in this process, MERTK and TYRO3, and saw that they were significantly decreased at the mRNA level with bilirubin treatment. I thus optimized an assay to track efferocytosis using the IncuCyte imaging system. In this assay, we feed bone marrow-derived macrophages with dead tumor cells that are dyed with a marker that emits a bright red light in the high pH of the macrophage lysosome. So on the images here, any of these small round cells are tumor cells, and any of these elongated bright red cells are a bone marrow-derived macrophage that ate a dead tumor cell. And we can track this red signal with time and see that this is significantly decreased with bilirubin treatment, suggesting that bilirubin in the microenvironment could be increasing macrophage immune suppression, but also decreasing macrophage function. So to understand whether or not this might be impacting metastasis, I turned back to the 6/6-CL4 mammary carcinoma model and introduced these cells into syngeneic mice into the mammary fat pads, waited until tumor volume reached about 80 millimeters cubed, and then began daily oral gavage with saline control or the HON inhibitor tinmesoporphyrin. At endpoint, I then collected primary tumors in lungs with formalin fixation and paraffin embedded them in order to look at the microenvironment through a series of immunohistochemistry and multispectral fluorescent stains. In this model, HON inhibition did not impact primary tumor growth. However, when we looked at metastatic burden in the lungs of mice using hematoxylin and eosin staining, while we didn't see a change in the number of metastases, we saw a significant decrease in the metastatic area with HON inhibition, suggesting that HO1 might be playing a role in metastatic outgrowth in this model. Additionally, we're currently characterizing the microenvironment in the lungs and primary tumors from these mice. And unfortunately, I don't have quantified data to share with you today, but I do have a representative image from a multiplex panel that we've developed, including the anti-tumor macrophage marker INOS and the pro-tumor macrophage markers arginase 1 and CD206, as well as the overall macrophage marker F480. And here's a representative image from the lungs of a mouse that was treated with the HO1 inhibitor tinmesoporphyrin. And you can't even see the F480 signal here very well because these macrophages are so strongly positive for INOS. This suggests that potentially the microenvironment of HO1 inhibited lungs might be more anti-tumor, and that could be why we're seeing a decrease in metastatic burden in these mice. Although, of course, we do need to go back and quantify this data for all the mice in our cohort, and we're also building upon this panel to add some of the functional markers that I've been mentioning today, like MERTK. With that, I'll conclude by saying that HO1 and its metabolite bilirubin may support lung metastatic progression by enhancing macrophage immune suppression and dysfunction via the metabolite bilirubin. There are a number of future directions for this project, including understanding whether or not these bilirubin-induced macrophages can functionally suppress the activity of T cells in the microenvironment. I'm also interested in further exploring the impacts of global HO1 inhibition, but also tumor cell-specific inhibition on the microenvironment of lung metastases, and I'm expanding this work to also look at liver metastases. And this includes further characterization of macrophage location, as well as expression of immune suppressive and functional markers. Additionally, I'm interested in further understanding the mechanism of action of how bilirubin is impacting macrophages, and whether it's potentially doing this by acting as a ligand and binding to a receptor in macrophages or through another means. And with that, I'll throw up my acknowledgement slide today, and I would love to take any questions.
Great, thanks very much, Michelle.
Yeah.
We start with, okay, I'm going to read up some of the questions in the chat here. It was, this is me, very interesting talk, thank you. First questions from Mehdi Shai. How can you rule out the effect of iron and carbon monoxide resulting from HO inhibition of metastasis versus bilirubin, as they're all metabolites of heme catabolism? And then maybe I'll just link it into the next part of his question. What do you think is upstream of heme catabolism? CD163, CD91, or TLR4? And then he says, great talk.
Yeah, certainly currently in the mouse models, we can't rule out with the experiment that I showed you the impact that the other heme metabolites might be having on metastasis. And there's, a lot of great data coming out now about the impact of iron in the tumor microenvironment. However, at least in vitro with our bilirubin rescue experiments, it suggests that a lot of the impact that we're seeing is through bilirubin. And we can also go back into the mouse models and do a rescue and treat them with bilirubin, which is something I'm interested in doing in the future. And then in terms of what's upstream of heme oxygenase 1, at least in the tumor cells, we know that this is a mechanism that's regulated by EMT. And we have shown that heme oxygenase 1 is regulated by the microRNA miR200C, and it's been shown in other models to directly bind to and degrade heme oxygenase 1 mRNA. Although we don't know currently in macrophages, because they also express heme oxygenase 1, what is regulating this pathway.
Okay, next questions from Deborah Vendramini Costa. And she says, very interesting. Did you consider depleting the macrophages in your treated versus untreated animals so that you could conclude that the effect you're seeing is from TAMs being more immunosuppressive? And she also asks, would bilirubin have an effect on other cells in the microenvironment? I guess so, right?
Mm-hmm. Yeah, that is a great suggestion. And it's an experiment that we're actually setting up hopefully in a couple of weeks to do this in combination, the HO1 inhibitor in combination with macrophage depletion. And then in terms of other cells in the microenvironment, definitely think that bilirubin is not just impacting macrophages. I'm partial to macrophages because I think, they're the coolest cell type, no offense to all the other myeloid cells. So that's where I started with the work, but there's definitely evidence that it can also impact cytotoxicity of CD8 positive T cells and T regulatory cell expansions. Those are definitely cell populations I'm interested in delving into in the future.
Great. Okay, connect to that. This is the last question, and so we let people have a short break. How might you deplete bilirubin in vivo?
Yeah, I don't know that we will be able to deplete it entirely other than trying to decrease, HO1 activity. Certainly we can treat with bilirubin to restore it. So it's not a perfect model, but
no, yeah, it's probably, yeah, I could imagine the side effects of that would be. Okay, I see that Jen has come back on, which means that she's going to give us some housekeeping information, I expect. Before that, thanks very much to all of the speakers of this session. It's been wonderful. It's been great discussion. And we're all enjoying it very much. And just a friendly reminder also for you, Michelle, if you can go back and answer any questions that you didn't get a chance to answer live. Thanks.
Great. Well, thanks so much. Judy, you put up the next set of talks. I think we can still come back at 1:15, give us about a 15-minute break. Does that work, Dimitri and Judy?
I think that's
he is DMARE Family Chair in Immunotherapy and Assistant Professor at Surgery from University of Miami and Sylvester Cancer Center, Associate Director of Translational Research. He is actually a pancreatic surgeon, but he's doing something which very difficult to do, to combine his surgical activities with the basic research, basically translational research. focusing on understanding how tumor intrinsic transcriptional programs regulate innate immunity. So I think that his data is quite exciting. I had a privilege to see some of them. And I welcome him here and looking forward to the presentation. And again, just a short reminder, please put your questions into the chat, and I will do my best to ask every question you ask, but try to be concise in your question. Then it will make my life a little bit easier. Josh, the floor is yours. Thank you. Thank you for joining us.
Well, thank you so much, Dr. Gabrilovich and the organizing committee for your kind introduction and this kind invitation to present. We're a young lab, and we're very excited to be here to present our work. So I have no relevant disclosures for this talk. Here's the outline of what I'll be talking about. It's really, taking a realistic and pragmatic viewpoint about the progress that we've made in pancreas cancer. I'm actually excited to give the first talk related to pancreas cancer at this symposium, where I think myeloid immunosuppression is one of the strongest, and dovetail that concept into understanding the hallmarks of therapeutic resistance. I'll try to connect the dots between the high-risk tumor genotypes and innate immune regulation, and then talk about one of the many cancer cell neutrophil circuits that sustain these immunosuppressive networks in the pancreatic tumor microenvironment that we have been working on and have recently published. So we'll start with the first one. I don't think it should be any surprise to anybody in the audience that pancreas cancer is a lethal malignancy. And our recent celebration of 5-year survival in pancreas cancer, eclipsing double digits, should be a sobering reminder of how exactly lethal it is. And even though we've made progress, we've improved chemotherapy. These are recent trials in patients with advanced pancreas cancer that have established multiple combination chemotherapy regimens that are important. I think it's important for us to frame the clinical problem. We've made advances in radiation, and we've made advances in surgery. I'm a surgeon. I take care of patients, and we do complex operations safer. We can replace venous anatomy and arterial blood vessels. We can do these operations robotically. We can move all the chemotherapy up front to increase the amount of total therapy that patients get. And we can do complex operations by taking some or all of the pancreas, reconstructing all the blood vessels. Here are 3 operations that I've done in the last couple of months. But I will be the fastest and the quickest to say, very humbly, that the war on pancreatic cancer is not going to be won in the operating room, or by rearranging the deck chairs on the Titanic, by changing chemotherapy regimens, or by delivering radiation more precisely, but by deeply understanding the molecular foundations and targeting its hallmarks of therapeutic resistance. So what are they? There's many, but in my mind, I distill down the hallmarks of therapeutic resistance in pancreas cancer to 3 main pillars. One of them starts with the tumor intrinsic genome. And it's a genomic landscape that's dominated by the cooperativity between KRAS and P53 mutations, as you can see in this word cloud from the TCGA. Pertinent to this audience and our talk today, you'll hear a lot about our work in understanding the profoundly immunosuppressive tumor microenvironment that's characterized by high prevalence of innate immune myeloid populations, particularly neutrophil-derived myeloid suppressor cells, as well as M2-like macrophages that impair T-cell infiltration and activation, and a particularly intriguing part of the pancreas tumor microenvironment, which is this concept of stromal inflammation, whereby the tumor stroma is not just a collection of extracellular matrix, but really living, breathing organisms that are the cancer-associated fibroblasts that act as cellular antennae to imbibe cues from the tumor microenvironment and amplify these signals to not only accelerate innate immune chemotaxis, but also sustain chemo-resistant IL-6 STAT3 signaling, predominantly through polarization of these pro-inflammatory or cancer-associated fibroblasts, or ICAFs, that have these properties that you can see on the slide. But looking from a bird's eye view, though, how these genomic alterations that define pancreas cancer tumorigenesis and dictate its immunosuppressive biology, promote stromal inflammation, and govern therapeutic resistance really remains poorly understood, exposing this critically underexplored genotype-phenotype chasm in this disease. And my interest in RAS P53 cooperativity goes back to my time when I was at Sloan Kettering as a as a surgical oncology fellow, where we wrote a series of papers where we not only established in multiple GI cancers the cooperativity between RAS and P53 and its association with poor survival, but also as a model to investigate mechanisms of innate immune regulation. And when I started my laboratory at the University of Miami about 3 years ago, we tried to recapitulate these findings in pancreas cancer patients treated at our institution. As you can see from this oncoprint, a vast majority of patients have cooperative tumors, cooperative mutations in KRAS and P53. And in our patients and in 2 other independent data sets, we were able to show that patients who had KRAS and P53 co-altered tumors did worse than patients with either RAS altered or P53 altered tumors alone. And then we went to the immunophenotype to see whether or not we could establish a clinically relevant model to study innate immune regulation, and using the immune deconvolation in transcriptomes of patient tumors, we found that there was a significant enrichment of myeloid populations, particularly macrophages and neutrophils, and an exclusion of CD8 T cells in RAS P53 co-altered pancreas cancers. And we were able to recapitulate this in high fidelity mouse models that either harbor KRAS and P53 alterations or RAS alterations alone. And so this really set up this clinically relevant model where we were trying to understand the intersection between this high-risk genome and this innate immune enriched and T-cell excluded microenvironment. And our next job was to connect the dots between this chasm from point A to point B. And that's what I'll start talking to you a little bit about. What are the cancer cell intrinsic factors that mediate this innate immune enriched and T-cell excluded phenotype? And what is the bidirectional molecular dialogue between those innate immune cells and cancer cells and fibroblasts that dictate stromal inflammation and therapeutic resistance? And so we started with the cancer cell intrinsic transcriptome, where we turned to single cell RNA sequencing data by comparing mouse pancreas cancers that either harbored KRAS P53 alterations or KRAS mutations without P53 alterations that you can see on the slide here. And when we compared the transcriptomes, we found a significant enrichment of innate immune pathways that are bolded here in the pathway analysis that were differentially upregulated in KRAS P53 cooperative tumors. And when we distilled down the specific transcripts from these pathways, we were intrigued to see multiple interesting candidates, but CXCL1 caught our attention for several reasons. But in parallel, we were looking at human pancreas cancer transcriptomes that were differentially upregulated in KRAS P53 tumors compared with RAS altered non-P53 altered tumors, and we found the same transcript, CXCL1. And for this audience, and I'm sort of alluding to the talk that was given by Dr. Barry earlier, and some of even the other talks that alluded to this, CXCL1 is part of the ELR chemokine of chemokines that interacts predominantly with myeloid cells, and particularly CXCR2 positive neutrophils. And so we went to a mass proteomics platform that we've developed at our institution with imaging mass cytometry using the Hyperion platform. And we asked 2 simple questions. Is CXCL1 upregulated in the epithelial compartment of RAS P53 tumors? And is it more so in RAS P53 tumors than in other cancers that express RAS but do not express P53? And that's what we showed here, where we showed here in the tumor cell islands that express pancytokeratin, we saw increased expression of CXCL1 compared with RAS tumors that didn't express P53, as you can see with the single cell segmentation here. And then we've gone on to do multiple studies that, hopefully will, that this paper will be out soon, that I'll direct you to, where we've been able to, in an isogenic model, upregulate RAS and P53 signaling to see the transcriptional regulation of CXCL1. And we show that this is predominantly to a phospho-CREB dependent mechanism. And we show using chip sequencing that CREB co-occupies the promoter of CXCL1 with RNA-POL2, and we've knocked this down in human organoid cells to show that this is transcription regulating CXCL1. But the real question is, how do we connect the dots from this cancer cell intrinsic transcriptional program with CXCL1 as a really interesting candidate to this innate immune microenvironment? And this is work that I'll be showing you that's been done by an extremely talented graduate student in my laboratory, Anna Bianchi. We first turned to human pancreas cancer patients and their single cell RNA sequencing data, and we asked, what is the interacting partner with tumor cell encoded CXCL1? Should not be a surprise to members of this particular audience that CXCR2 and that CXCR2 is expressed squarely in the neutrophil or the neutrophilic myeloid-derived suppressor cells in the pancreas tumor microenvironment in patients. But what are the spatial implications of this interaction between tumor cell-encoded CXCR1 and CXCR2 positive neutrophilic MDSCs and its impact on T cell exclusion? To do this, we went back to our mass imaging cytometry platform, and we expanded our panel to include multiple different cell types, but I'll just call to your attention pan-cytokeratin or cancer cell islands that express CXCR1, CXCR2 expressing tumor-infiltrating neutrophils, multiple different myeloid populations, stromal populations, and CD8 T cells. And what we asked very specifically are, what are the predicted cellular relationships in terms of contiguity, that means how close the cells are, and exclusion, that means how far the cells are in the tumor microenvironment that are dictated by these spatial interactions. And what we were really excited to see is that when you look at the spatial distance using this single cell segmentation platform from pan-cytokeratin expressing CXCR1 expressing tumor islands, we saw that they were spatially highly contiguous with CXCR2 neutrophilic populations and excluded from CD8 T cell populations. And this is an elegant way not just to understand the spatial insights into this biology that connects the dots between the associations I showed you before between RAS and P53 cooperativity, tumor cell encoded CXCR1, neutrophil abundance, and T cell exclusion, but really lays the foundation for deeper mechanistic investigation. So to do this, we took a RAS and P53 cooperative cell line in conjunction with our collaborators at the University of Pennsylvania, Ben Stanger's group. We were able to knock out CXCR1 using CRISPR-Cas9 technology. And when we orthotopically injected these in tumor-bearing mice, we saw a profound arrest of tumor growth. And when we wanted to understand the molecular basis of this in a very amazing phenotype that we saw in these tumors, we performed bulk RNA sequencing. And as you would expect, by knocking out a chemokine that interacts with the innate immune system, we saw profound downregulation of multiple different pathways related to innate immune regulation, such as TLR signaling, NETs, neutrophil degranulation, etc. But one head-scratching finding that we had at the time, which we couldn't explain, was the strongest pathway that was downregulated was actually TNF signaling. And this was particularly head-scratching to us at the time because we saw a massive invigoration of adaptive immune cells and an invigoration of T cells in the tumor microenvironment, so much so that silencing CXCR1 really turns these tumors from immune cold to immune hot. You can see here from the Wisny plot, it's a massive infiltration of CD4 and CD8 T cells. And not only that, when we took this model and we either knocked out T cells using a neutralizing antibody or performed these in CD8 transgenic knockout animals, we saw that this latency of tumor growth that was imparted by the loss of CXCR1 in the cancer cell compartment was really lost when you abrogated CD8 T cells. But remember, I told you, and you all know that CXCR1 interacts with the innate immune compartment. So what's happening with the trafficking and the function of these? So what we learned was when you silence CXCR1 in the cancer cell compartment, this mediates this dramatic immune remodeling by not only altering the trafficking dynamics, I don't have time to show all that data, but really fundamentally alters the immunosuppressive potential of the neutrophilic myeloid-derived suppressor cells, as you can see from significantly reduced expression of arginase 1, myeloperoxidase, IDO in the tumors of CXCR1 knockout animals compared with wild-type animals. And it also significantly disrupts this an activated gene module that is associated with potent T cell suppression that was published by Dr. Grabilovich's group recently, and that is typified by strong expression of CD14. So much so that when we isolated these neutrophils from the orthotopic tumors of these animals, and this is not a mean task for those that work with pancreas cancers, and we did T cell co-culture assays, we saw a profound suppression of T cell activity with the wild-type MDSCs. But this was rescued when we co-cultured T cells with MDSCs that were isolated from CXCR1 knockout animals. Really, this was intriguing to us, and this suggested to us that there was a co-evolution of tumors and immature neutrophilic myeloid populations whereby tumor cell intrinsic transcriptional programs elaborate factors that not only beckon these cells to the tumor microenvironment, but they also sculpt a functional program that governs their fundamental behavior in these tumor sites. So we wanted to understand what those underpinnings were. And so here is a model where we are starting to connect the dots between the high-risk genome and this neutrophil-mediated signaling. And we've filled in some of the gaps here. And we think that we can link KRAS cooperativity via CREB-mediated mechanism to tumor cell-encoded programs such as CXCR1 that then interacts with innate immune cells. But we wanted to understand next, what were the neutrophil intrinsic mechanisms that underlie this immunologic rewiring? And to do this, we isolated neutrophils from wild type and CXCR1 knockout animals, and we subjected them to bulk RNA sequencing, and we performed IP analysis to find that the top predicted regulator of a neutrophil function was actually TNF. And then some light bulbs started going off, and based on that other observation that I mentioned to you, the strongest dysregulated pathway comparing the two transcriptomes was actually MAP kinase signaling. And when we distilled the different transcripts that were associated with MAP kinase pathway that were dysregulated between wild type and CXCR1 knockout neutrophils, lo and behold, we found TNF. And when we treated tumor-bearing animals with a MEK inhibitor, which is abrogates MAP kinase signaling, obviously, we found a reduction in TNF signaling in CXCR2 positive, but not CXCR2 low PM and MDSCs, suggesting that there was a mechanistic link between the two. We've gone on to show that this mechanistic link downstream of CXCR1 and CXCR2 ligation is through an IKKB MAP3K8 mediated mechanism for TNF regulation. I just don't have time to show all that data. But this myeloid or neutrophil specific TNF phenomenon may not be that surprising to many of the myeloid immunologists on the call who are aware of the role of myeloid-derived TNF in chronic granulomatous disease, for example, other inflammatory diseases. But leveraging those lessons, we really asked ourselves, is this relevant in pancreas cancer? So we went back to our human pancreas cancer single-cell RNA sequencing. We asked, what is the cell type that produces the most TNF? Here we show that this is also neutrophilic myeloid-derived suppressor cells. We went to our mouse single cell. Which population expresses TNF? Neutrophil myeloid-derived suppressor cells. And we pulled these out and we put them on a cover slip with polylysine, and we did a confocal microscopy, and we showed that TNF is expressed in these neutrophils. And when we took pancreas cancer patients that were being treated at our institution that were treatment naive, and we got PBMCs from them, and we did flow in their circulating cells, we found that compared to all other immune populations, I'm showing only 6 here, that the MFI for TNF was highest in neutrophilic MDSCs, and specifically in CXCR2 positive neutrophilic MDSCs. And so this was an aha moment for us. Because remember, I showed you that TNF signaling was significantly downregulated in CXCR1 knockout tumors. And we think that we have uncovered this paradox in which inhibiting CXCR1, CXCR2 engagement invigorates T cell activation despite dampening tumor-wide TNF signaling, as you can see here, from both CXCR1 knockout animals as well as animals treated with the CXCR2 inhibitor, AZD5069, which you heard from Dr. Barry earlier, mostly through disruption of neutrophil-restricted TNF, as you see from the intratumoral neutrophils pulled out from each of these tumors, where TNF is gone. So now we're starting to get a clearer picture that perhaps some of the mechanisms linking and some of the central regulators of this immunologic rewiring may be neutrophil-derived TNF. And we've done several experiments where we showed this mechanism is mediated through a transmembrane TNFR2 dependent mechanism, and not so much a soluble TNFR1 mechanism. I'll show you some of that data in a second. And this is mediated through a MAP3K8 mediated mechanism. But let me pivot for just 1 second and go back to those hallmarks of therapeutic resistance that I showed you before. Remember, I mentioned that inflammatory CAF polarization and stromal inflammation was a major hallmark of therapeutic resistance. Well, in parallel with the discoveries that we were making with neutrophil intrinsic TNF, we were also uncovering a novel relationship between neutrophil abundance and their spatial proximity to cancer-associated fibroblasts and stromal inflammation and its downstream consequences on chemoresistance in pancreas cancer. So here's a paper we published last year in eLife, where we showed that tumors that started off with high neutrophil to lymphocyte ratios not only had higher stromal density, but were more chemoresistant, had poor response to chemotherapy ultimately when we took these tumors out after giving them chemotherapy prior to surgery in the operating room. And then when we modeled this in the mouse, we showed that we could potentiate chemosensitivity by attenuating neutrophil to lymphocyte ratios. And that in part, this was related to a mechanism where we saw reduced inflammatory CAF populations in the tumor microenvironment in mice in whom the neutrophil to lymphocyte ratio had been attenuated in combination with chemotherapy. So then we, based on this, to try to tie the two stories together, we simply asked the question, does neutrophil-derived TNF instigate inflammatory CAF polarization and stromal inflammation? We've done a series of experiments, but I'll just show you the Cliff Notes version of this, where we isolated intratumoral neutrophils and we co-cultured them ex vivo with cancer-associated fibroblasts, and we assayed for the canonical inflammatory CAF markers CXCL1 and IL-6, and we blocked both aspects of TNF signaling, either with etanercept, which is a Fc decoy of TNF-R2, or a soluble TNF inhibitor X1595. What we saw was really, really exciting to us. Not only did we see that intratumoral MDSCs upregulated both CXCL1 and IL-6, suggesting that they promote an inflammatory CAF phenotype, which has been shown really for the first time in pancreas cancer, but that there is a divergence in the relationship between what kind of TNF signaling comes from the neutrophil when we precondition them with either TNF-R2 inhibitor or a soluble TNF inhibitor, where in the TNF-R2 inhibition, we see a rescue of the phenotype. However, in TNF-R1 inhibition, a soluble TNF inhibition, we see an accentuation of CXCL1 and IL-6 expression. So this was really exciting to us. And so then we took this in vivo and we've developed a pharmacologic strategy to do pulsatile dosing of etanercept that allows adaptive immune recovery. And when we did, when we assayed these tumors in tumor-bearing mice treated with etanercept versus vehicle control, we saw, just to recapitulate what I showed you in vitro, a significant amelioration of the ICAF to the myofibroblast to CAF ratio. And we also were able to show, interestingly, that we were able to attenuate some of the immunosuppressive myeloid populations and invigorate T cell activation. And that what was more interesting to us was that there was a 5-fold increase in the interferon gamma production by the intratumoral T cells in these models. And we have lots more data I just don't have time to get into, but I hope that I've been able to convince you that targeting the central node that emerges from neutrophil-mediated TNF signaling, and particularly transmembrane TNF-R2 signaling from the neutrophil, and its disparate effects on other cellular constituents in the tumor microenvironment, seems to overcome some of the hallmarks of therapeutic resistance we've talked about, by reducing myeloid cell enrichment, by overcoming T cell exclusion, and by reducing inflammatory CAF polarization. So we took this in vivo and we combined this with standard of care chemotherapy in our tumor-bearing mice models. And although the monotherapy arms showed no difference, as we expect to see, we saw a profound improvement in the survival of these mice that were primed with TNF-R2 inhibition and then treated with chemotherapy, suggesting that this was a priming of the microenvironment followed by chemosensitivity type of mechanism. And a lot of this work, again, done by two incredibly talented people in our laboratory, Anna and Iago. And so overall, I hope I've been able to show you that there is this cancer cell neutrophil circuit in the pancreas tumor microenvironment, and we're trying to fill in those gaps. Neutrophil-mediated TNF may have direct and indirect consequences on T cell activation, but more excitingly, we think that they have effects on promoting stromal inflammation by not only upregulating CXCL1, which sustains this circuit between tumor cell encoded CXCL1 and the CAF encoded CXCL1 and keeps this circuit going, but also promotes IL-STAT3 signaling to increase chemoresistant circuitry in the tumor microenvironment. And we're very proud to say that this paper was just accepted in Cancer Discovery, and we hope to have this out soon to share with the members of this group. But I just want to take one more minute to go a little bit deeper and just show you where we're going with this next. We obviously have not shown any data so far that this is a neutrophil intrinsic TNF dependent mechanism. And so we've generated a mouse model where we have conditional silencing of TNF within the S100A8 promoter. And when we inject orthotopically tumors in this model, we see a profound reduction of tumor growth, which was very, very exciting to us, almost recapitulating what we saw in the CXCL1 knockout animals, if you remember that one slide. What was also interesting is that we've seen amelioration and reduction in stromal inflammation in these mouse models. And also very interestingly, we see a reduction in tox expressing CD8 T cells and memory progenitor a significant increase in memory progenitor T cells that are typified by CD127 positive KLRG1 negative T cells. So we're really excited to move this forward and to understand the mechanistic underpinnings of why myeloid TNF is working in a central regulatory fashion in the pancreas tumor microenvironment. So with that, I'll acknowledge all the members in the lab, our intramural and extramural collaborators, our funding sources, and our overall group. And I really want to thank Dimitri for the invitation to present our work here today. I'll take questions.
Thank you very much, Josh. It was very interesting. There's a lot of food for thought. There are several questions I would like to pass on you. But I will ask a very quick question myself. Your neutrophil/PMN-MTC interaction with fibroblast, you just focus on cytokines released by fibroblast. What happens with the major function? Release of extracellular matrix, proliferation, characterization of Maya versus inflammatories, some kind of basic things.
Yes, great question.
And Josh, please keep your answer very to the point, just we don't run out of time.
Yeah, we've shown this in the paper. There's incredible stromal remodeling that happens, reduction in serous red, trichrome blue, reduction in extracellular matrix, reduction in you know, a lot of the fibroblastic functions. Okay.
So it's a question from Judy. Have you tried to block both CXCR2 and TNFR2 in mouse model of PDAC?
We have not done that, but we can. I'm happy to talk offline as to why I'm not certain that that's probably the best way to synergistically move forward in this space. But it's an interesting suggestion.
Okay, another question. I have the impression that ICAF tend to be anti-tumor, while MyCAF are more pro-tumor. So wouldn't prevention of ICAF polarization be actually problematic?
You know, well, the dichotomous model is problematic in general, but in general, our consensus in the field is that ICAFs are associated with chemoresistance in pancreas cancer. But the dichotomous model is problematic. MyCAFs also have some other effects that are pro-tumorigenic.
Okay. More question. Why do you think CXCL1 is a dominant CXCR2 ligand? And also, what stage of KPC model were you using?
Yeah, thank you for that.
Yeah, go ahead.
Yeah, thank you for that question. CXCL1 is not, I don't think it's the dominant ligand. There are others. And in fact, we have pharmacologically blocked CXCL1, which is why we're not pursuing that as a therapeutic option here, because we see compensatory increase in other ELR chemokines that ligate with the CXCR2. We've used all sorts of stages here. The genetic engineered data you saw was not in the KPC model. It was in a PKT model, which is a TGF receptor beta 2 flux. But we've used early and late KPC orthotopic systems to show our work.
So the second question, was it late stage disease, early stage of the therapeutic intervention? It's basically a continuation of that question. And what stage you treat them?
Yeah, that's a great question. So we start at a you know, in the orthotopic setting in an early time point, and we prime the tumor microenvironment with our pulsatile dose of etanercept. So you know, basically all the changes that I showed you, we believe will basically prime the microenvironment for chemosensitivity and perhaps chemo and immunosensitivity in the future. But that's why, again, as a surgeon, this is why it's provocative for us, because we want to bring these therapies into the neoadjuvant space where there's intact antigen and tumors are not widespread all along the liver and with multiple variegated mechanisms of resistance.
Right. This makes sense. All right, we are right on time. We have a chance for one burning question. If not, I will give the floor to Jody and Josh. Thank you very much. It was very insightful. Thank you.
Thank you.
Oh, just one last question, Jody. We still have 1 minute.
Okay.
Do you see, just pop up on my screen. Do you see increases in Tregs? Oh, someone interested in Tregs in myeloid meeting. Since more what's a shame? Since more TGF beta probably from MyCAS?
Yeah,
MyCAS,
yes.
yes.
That's a
not
great
cut.
question from Dr. Vendramini Costa. So actually, we see actually with the etanercept treatment and with subsequent other pharmacologic strategies we are developing to target TNFR2, we see a reduction in Tregs, because as you know, Treg biology is driven predominantly by TNFR2 signaling. And so I have not dissected out the specific contribution of TNFR2 autonomous to Tregs versus paracrine CAF Treg crosstalk through TGF-beta, but that's a great point.
Wonderful. Thank you, Josh. Jody, the floor is yours.
Okay, thank you very much for that great talk. So now we'll move to our next speaker, who is Asaf Maus from the Dana-Farber Cancer Institute in Mass General Hospital, where he's a postdoctoral fellow also at the Whitehead Institute. And his talk is Unbiased Phenotypic Screens Identify IL-10 as an enhancer of macrophage anti-tumor responses. So thank you.
Thank you so much. Hopefully you can hear me and see my slides.
Yes.
Perfect. So thanks for the opportunity to present here today about how we can potentially enhance macrophage-based immunotherapy with cytokines. As Dr. Varner mentioned, I'm a medical oncology fellow at the Dana-Farber, and I'm doing my postdoctoral work at the Weisskopf lab. And I just wanted to put a shout out here that we are looking for additional people to join the team. So if you're interested in the work we're doing or using macrophages for bettering human health, feel free to reach out to me or to Kip. These are my competing interests. So this is a great forum to talk to about the downsides of T-cell immunotherapy. When I see patients in clinic that have metastatic disease, I typically have to tell them that the disease is incurable. There is a subset of patients that can benefit from T-cell directed therapies and can even think about or talk about long-term remission or cure, but that's the minority. And at the same time, I have to talk to them about severe and life-threatening toxicities that when you go through that with a patient, that really leaves a mark on you. So macrophages are ideal candidates to improve on cancer immunotherapy. They're found essentially in all tumors. And even though they're considered to be bad actors by many in the field, they can engulf and kill cancer cells and direct it towards anti-tumor immunity. Now, the best characterized checkpoint is the CD47 SIRP alpha axis. CD47 on the cancer cells interact with SIRP alpha to prevent phagocytosis. We call this a don't eat me signal. And when this interaction is prevented when the anti-CD47 antibody, then there is phagocytosis of cancer cells. But what we're seeing from clinical trials is that single agent anti-CD47 isn't enough in broad strokes, and that combination strategies are really needed. And so that's what motivated us to turn to cytokines. Cytokines, like Dr. Caffarel mentioned, have pleiotropic activities. They can work on a multitude of cells and various cellular processes. And so they've been involved or implicated in carcinogenesis as well as cancer control. So we decided to use an in vitro model to look at how cytokines may affect macrophage activation. We took GFP positive cancer cells, PC9 cells, which are lung cancer cells in our model, and macrophages that we differentiated from human monocyte donors. In this arm of our screen, we included CD47 blockade to activate the macrophages, and we added a curated cytokine library of 113 recombinant cytokines, and this is the team from the initial screen here. And so we co-cultured them for 7 days and used automated microscopy and image analysis to see how these cytokines affect cancer cell growth. And if you want to learn more about the screening platform and a very cool story from our lab that was led by our technicians, Kyle Vaquero and Jules Allen, you can check out this QR code or go to bioRxiv. But I just want to show you 2 representative movies from this screen. This is what happens in control wells where the cancer cells will fill up the entire well. And this is what happens when you add CD47 blockade. You can't see the macrophages because they're not labeled, but they're chewing away at the massive cancer cells and kind of corralling them into a corner. So in our cytokine screen, we found surprisingly that interleukin-10 actually enhances macrophage inhibition of cancer cell growth in response to CD47 blockade. On the left here, you can see the growth curves from all the cytokine conditions, and highlighted is control in black and IL-10 in blue. And on the right here, you can see the volcano plot from the very last time point, highlighting the hits on our screen. And I say surprisingly because IL-10 has largely been implicated as a quote-unquote M2 cytokine that drives macrophages in the tumor microenvironment towards a tumor-promoting, invasion-promoting, and metastasis type phenotype. And even in vivo models where IL-10 or pegylated IL-10 has been shown to be effective against tumors, it's thought that it's doing so by activating CD8 T cells, but still thought to inhibit macrophages from exerting an anti-tumor effect. And we've looked at this with multiple donors now, and there is some donor-to-donor variability, but at the end of the day, what we see is that when you add IL-10 to our co-culture assay, there isn't really an effect as a single agent, but when you add it onto CD47 therapy, that elicits a very potent anti-tumor response. And again, these are representative images from the control. IL-10 looks very similar to this. This is anti-CD47, and this is the combination therapy. So we wanted to look at another assay and see if this combination specifically increases phagocytosis. We took macrophages and primed them for 48 hours with either IL-10 or control. And then we co-incubated them with labeled cancer cells for 2 hours with or without anti-CD47 and measured phagocytosis. This is a standard assay in the field. And what we see here is that for at least 4 different cancer cell lines of colon and lung origin, the combination of IL-10 and anti-CD47 results in the maximal phagocytosis. And in some of the cell lines, IL-10 by itself also enhances phagocytosis, which is to some degree consistent with the literature. And we don't have a lot of time to discuss this today, but we looked at murine models as well in vitro. And we saw here, I'm presenting a phagocytosis assay where, again, the combination of IL-10 and CD47 here in green, both for a colon cancer cell and a lung cancer cell line, the phagocytosis with the combination is also maximal in comparison with the other conditions we looked at. And so our next question was, if we're seeing enhancement of anti-CD47 blockade with IL-10, will we see this with other antibodies? And we looked at 2 separate antibodies. One was an anti-EpCAM antibody, essentially targeting an epithelial cell marker that only opsonizes the cancer cells. The other was cetuximab, which targets EGFR, which are cancer cell line expresses. And so in both of these instances, we see that adding IL-10 to an opsonizing antibody does activate the macrophages to kill more cancer cells. So if this is a more generalizable phenomenon, we thought that it is likely that this is working through the Fc receptors that is on macrophages and can sense immunoglobulins. And so we first looked at IL-10 regulation of Fc receptors, and we saw that for CD16, 32, and 64, the main activating Fc receptors, there is upregulation by IL-10 seen here in green in these 3 plots. And so we next wanted to use our co-culture assay, again, co-culturing macrophages and cancer cells for multiple days, but this time inhibiting the 3 activating Fc receptors, CD16, CD32A, and CD64. And when we did this, we saw that only when we inhibited CD32A did we get abrogation of the effect of anti-CD47 and the effect of anti-CD47 and IL-10. So this is early clues, and we're obviously exploring further mechanistic explanations for how IL-10 is enhancing anti-CD47 activity. Finally, we wanted to look at in vivo models. And so what we did, we took, for this model, we took the human cancer cell line that we did our screen with, and we overexpressed either interleukin-10 or a control vector with a lentiviral vector. The cells underwent puromycin selection, and we then injected them into the subcutaneous tissue of NSG mice. As you know, NSG mice lack an adaptive immune system and also NK cells. So essentially their immune system is a myeloid immune system. And we see very good recapitulation of what we saw in our long-term co-culture assay, where IL-10 overexpression by the cancer cells doesn't really affect their growth. There is activity of anti-CD47, but the combination of anti-CD47 against cells that overexpress IL-10 resulted in the best tumor response. Now, we do have additional encouraging data from syngeneic models, but it's a bit early to present it at this point. So in conclusion, I hope that we showed you that interleukin-10 enhances macrophage cytotoxicity towards cancer cells in response to CD47 blockade, but not only, also in response to opsonizing antibodies, and that the combination of IL-10 with CD47 blockade enhances macrophage phagocytosis of cancer cells and is active in vivo, so could potentially be translated into clinical trials. A lot of work still to do in terms of figuring out the mechanism and the contexts in this, where this is most likely to be active, and we're excited about doing that work. So I just wanted to give a big shout out to people doing the work. Kyle, Juliet, and Jose, 3 technicians in our lab, have done or participated in all of these experiments. I wanted to thank Bob Weinberg for co-mentorship, Ferenc for a lot of the animal experiments, and multiple other people that have guided me through this track. And more than anything, Kip, who's an amazing mentor and just a wonderful person to work for and with. And again, I'll mention that we're looking for additional people to join the team. So if you're interested, feel free to contact me on LinkedIn or Twitter, or contact Kip directly. I think he's on the chat for this meeting. Thank you very much. I'd be happy to take questions and hear feedback now or later.
Thank you very much for a very interesting talk. I have a question. So as you screened numerous cytokines, did you also identify other cytokines that might have a direct effect? And then I wonder whether you, you know, IL-10 is not exclusively an M2 type cytokine. It can also be upregulated in so-called M1 macrophages. So I wonder if you have looked further at this issue.
Yeah, so I mean, we do have an arm of the screen that is without CD47, and we do have a few hits that activate the macrophages in a direct manner to act against the cancer cells, as well as additional hits from the CD47 arm of the screen. So certainly there are additional hits. Some of them are context dependent, meaning that they work for some cell lines and not for others, which we know to be true about cytokines in general. And I'm blanking on your second question, sorry.
Well, I will say that we have noticed when we look at, say, PI3 kinase gamma inhibition in vivo, and it repolarizes macrophages, it interestingly also upregulates IL-10, but it also upregulates your classic M1 markers, and we see also in vitro. So I guess I'm just wondering if other chemokines that are classic M1 might also have some effect on the CD47 activity.
Yeah, so we're trying to look at this in different ways. We've obviously characterized kind of macrophages under different cytokine conditions and done proteomics to kind of get a in vitro quote unquote clean look at this. And we're also working to get single cell RNA sequencing from our syngeneic and our xenograft models to better understand what is going on and what other cytokines and other factors may be involved in what we're seeing.
So we have a couple of other questions. Is that, do you observe apharocytosis in your settings? Or just
We haven't looked, but I'm happy to chat with whoever asked and kind of see if that would be something worth pursuing. Yeah, well, we haven't looked.
Yeah. And then the other is, how do you overcome the immunosuppressive function of IL-10 on T cells in your in vivo model?
Yeah, so I mean, I think the effect of IL-10 on T cells is something that's been controversial, at least in the studies that led to the clinical development of IL-10, which ultimately didn't work, but in clinical trials. But in those studies, a lot of the data suggested that that IL-10 actually activates CD8 T cells to promote an anti-cancer effect, and that the net effect of IL-10 was anti-tumorigenic. But yeah, I think it's going to be important to tease out the contexts in which this is relevant and kind of tease it out more for sure.
Okay, so I'll ask one more quick question. Merging, so have you seen any effects of oncostatin M, IL-6, or on the effective anti-CD47 antibodies? And then also, have you looked at whether SIRP alpha expression changes in response to treatment?
We haven't looked at SIRP alpha, but certainly something that we're planning to do, and hopefully as a single cell RNA-seq will provide some of that information. Oncostatin M, at least in our system, had very variable activity depending on the donor. I mean, all of the cytokines have variability, inter-donor variability, but oncostatin M specifically for us, in between different human donors, had a large amount of variability, so we haven't pursued that as much.
Okay, well, thank you very much. If you could take a look at the chat and interact directly with the question answers, that would be great.
Thank you so much.
Thank you. Our next speaker is Brenda O'Connell, Director of Translational Science at Infinity Pharmaceuticals. And she will talk about eganelisib, the potential first-in-class PI3K gamma inhibitor for macrophage reprogramming in cancer. Is Charlene Lau. She's President and CEO of Immune Onc Therapeutics and will tell us about the novel myeloid checkpoint inhibitors her company is developing as a next generation cancer immunotherapy. Welcome.
Thank you, Judy. Can you hear me?
Yes.
Okay, good. Thank you. It's my pleasure to introduce the pipeline of Immune Onc Therapeutics. Our goal is to develop next generation cancer immunotherapy by targeting novel myeloid checkpoint targets. Immune Onc started in operation in 2016. We are almost 7 years old. We are currently a private clinical stage biotech company headquartered in Palo Alto, Northern California. We are proud of our strong science, and that is witnessed by our strategic partnerships, including the investment from the Leukemia and the Lymphoma Society, multiple grants from the National Cancer Institute and California Institute of Regenerative Medicine, and clinical collaborations with Regeneron and Beijing. We have built an experienced team, experienced in translational science and clinical development. We own worldwide IP to all of our assets. So for this audience who are very familiar with the translational and research issues in myeloid biology, I want to focus my talk more on the clinical application. The question and the problem we are trying to address are a resistance to T-cell checkpoint blockade, as shown here. And we all acknowledge in the myeloid network that the primary immune resistance and secondary immune resistance are largely mediated by myeloid checkpoints or myeloid cells. And in this case, by targeting the myeloid checkpoints with inhibitors or antagonistic antibodies, we believe we can address the needs of 3 patient populations. One is patients who have not experienced the anti-PD-1, PD-L1 due to lack of a robust response. We can enable a response in combination with the anti-PD-1, PD-L1. Second is we can work together to make the responding patient population bigger or the duration of response longer. And then the third one is an emerging problem where patients develop resistance to anti-PD-1, PD-L1. And together with our myeloid checkpoint inhibitors, we can reinvigorate immune response and allow the patients to regain response. And we have seen that in clinic by us and by Merck. So this is a simple illustration of myeloid checkpoints as contrast to T-cell checkpoints. So the targets are primarily or predominantly expressed on myeloid cells. They do have the feature of a checkpoint with extracellular Ig domain and the intracellular immunoreceptor tyrosine mediated inhibition motif. Because of the ligands, multiple immune inhibitory ligands binding, the suppression is now delivered by the myeloid cells, causing a lack of a robust antigen presentation, for example. And if we have antibody to block the inhibitory ligands from binding, we can see increased antigen presentation that could potentially translate to a stronger signal 1, reprogram myeloid phenotype, release pro-inflammatory cytokines, attract and activate effector cells. This causes changes in the tumor microenvironment. So by this, you can see, and we heard even in the first keynote speaker, that myeloid checkpoint inhibitors are not expected to work as a monotherapy. They regulate T-cell checkpoint inhibitors, so they are optimally combined with T-cell checkpoint inhibitors. And the reason we choose LILRB family, the leukocyte Ig-like receptor family B, is these are a family of inhibitory receptors that are expressed primarily or predominantly in myeloid cells, and their ligands have been shown to inhibit the function of immune cells. We took a platform approach in collaboration with our academic collaborators at the University of Texas, Southwestern, as well as Houston, and developed 2 compounds to interrogate biology. And subsequently, ImmuneOnc has developed therapeutic candidate antibodies, including 2 in clinical stage, IO-108 and IO-202. So as you can see, IO-108 target LILRB2, also known as ILT4. IO-202 target LILRB4, also known as ILT3. And then we have a preclinical candidate, IO-106, targeting LINE1. For this family, other than LINE1, there is not a real one-to-one correlation of mouse orthologs. So a lot of translational work has been carried out by our scientists, and we have presented at multiple scientific conferences. Our posters are also available through our website. So today, by focusing on our clinical pipeline, I am very pleased to share a few highlights. So IO-108 target LILRB2. As we know, LILRB2 is actually expressed on a variety of myeloid cells, including monocyte lineage as well as granulocyte lineage, including neutrophils. And there are multiple cancer-relevant ligands binding to LILRB2. And this way, they promote tumor immune evasion and contribute to anti-PD-1 resistance. we have a therapeutic antibody that binds to LILRB2 with a high specificity and high affinity and blocks LILRB2's binding from multiple cancer-relevant ligands. In this way, we can reprogram the myeloid cells and turn on the tolerogenic environment into pro-inflammatory environment. Our antibody also has a distinct epitope and slower off rate, so potentially longer target engagement compared with the competitor antibodies. This is our clinical trial design in dose escalation, every 3-week dosing, either monotherapy or in combination with anti-PD-1, in this case, pembrolizumab. First cycle is the DLT period. We are very efficient in having 4 steps dose escalation, starting from 60 milligram, going all the way to 1800 milligram. And we can also start the combination therapy with anti-PD-1 once we clear the second dose. So this is going to be shared at an upcoming scientific conference. What I can summarize here, because we have the disclosed trial in progress data, is that all of the data we're going to present have been developed in the US. We completed those escalation and we have selected those for expansion cohort. We have not seen those limiting toxicities as a monotherapy or in combination with pembrolizumab. We have seen complete response as a monotherapy in multiple line T-cell checkpoint inhibitor treated patient. We have seen multiple partial responses and stable diseases as a therapeutic modality with our monotherapy or combination with an anti-PD-1. The exciting thing is to see clinical benefit correlated with baseline characteristics and post-treatment changes in the PD biomarkers. These support our therapeutic hypothesis and the mechanism of action. Furthermore, we also leverage biomarkers to guide our expansion cohort selection at the recommended phase 2 dose, and all of these cohorts are now open. And in fact, we have also opened the expansion cohorts in China, and we got support from Regeneron for the use of their anti-PD-1 in the US, and from Beijing for their anti-PD-1 in China. So now let me turn quickly to IL-2. This is also a very exciting program. In this case, LILRB4 is more narrowly expressed. It's only expressed on monocyte or monocyte-derived cell types. And in the case of acute monocytic leukemia, LILRB4 signaling in leukemia cells mediates T-cell suppression and tumor infiltration into extramedullary sites. This was a paper published by our UT collaborators with Immunonc's support. We now have multiple mechanisms of action with our IL-202 for leukemia. IL-202 is an IgG1 Fc competent humanized antibody. It blocks multiple ligands binding to LILRB4, including ApoE and fibronectin. And because LILRB4 in leukemia is also expressed on cancer cells such as AML blasts, we can utilize ADCC and ADCP to kill blast. And there are other mechanisms, primarily because of the immune checkpoint function. When we block this checkpoint, we actually reverse T-cell suppression. We turn the don't kill me signal into kill me signal by mobilizing T-cells to kill leukemia blasts directly. We also block leukemia cell infiltration, turning the don't find me signal into find me, so that the circulating blasts could be more sensitive to chemo. So we are also using IL-202 in combination with the standard care. This is a phase 1 trial that's ongoing. We are showing here dose escalation on the top as a monotherapy every 2 weeks dosing, but each cycle is actually 28 days with the first 28-day cycle as the dose limiting toxicity period. Showing the bottom is in combination with azacitidine, which is a hypomethylating agent whose approved treatment include a 28-day cycle, so that matches very well with our treatment cycle of every 2 weeks of our drug. So I will share with you the data highlight to the next slide. But we are also very pleased that IO-202 has a differentiated mechanism of action in solid tumors, so it can be utilized as a solid tumor therapeutics. In this case, IO-202 reprograms myeloid cells in solid tumors by synergizing with other immune activating signaling pathways, turning the tolerogenic monocytic myeloid cells into antigen presenting monocytic myeloid cells. And this also led to an ongoing phase 1 trial in solid tumor, where by leveraging the safe dose cleared in the leukemia trial, we are able to start at 250 milligram. And now here is the flat dose and every 3-week dosing. And after we cleared this dose, we also opened a combination cohort with Pembro. We are bringing IO-202 all the way to 2400 milligram flat dose in this case. So in summary, IO-202 is an antagonist antibody targeting RB4 with high specificity and affinity. We are pleased to see the promising data in the ongoing phase 1 trial supporting leukemia development strategy. Here, we don't see those limiting toxicities as monotherapy or in combination with azacitidine. We have seen complete response and partial response in relapse refractory AML. We have also seen partial response, marrow response, as well as clinical benefit in CMML, which is a rare leukemia. We now have 3 expansion cohorts open with IO-202 plus standard of care in first-line CMML, relapse refractory AML, and first-line unfit AML, with more refined patient selection in AML. And we have received the FDA orphan drug and fast track designation for AML. We are really very pleased with the progress. In the solid tumor trial, because we start with a reasonable dose level, we actually can see biomarker changes and receptor occupancy. And we believe IO-202 can also be potentially combined with anti-PD-1, PD-L1, or other immunogenic therapies for solid tumor. Now, quickly turn to IO-106. This is our preclinical asset targeting and LAIR-1. And in this case, LAIR-1's expression is slightly more broad, not only on myeloid cells, but also on lymphoid cells. And the high affinity ligand is collagen, so you can see binding of collagen to LAIR-1 leads to T cell suppression and exhaustion, as well as dendritic cell deactivation in the tumor microenvironment. So the mechanism here again is to use blocking antibody to block collagen mediate the immune suppression. We do have a high affinity antibody binding to LAIR-1, blocks interaction between LAIR-1 and the ligands. We have a typical antibody PK profile supporting Q3 dosing, Q3-week dosing in human, robust CMC process with high titer, and we have received the FDA favorable written response to our pre-IND questions. So it's all green light to IND. In summary, we are very pleased with the progress to advance our robust platform and pipeline with 2 first-in-class clinical assets, including IO-108 that target LIRB2 or ILT4, and IO-202 targeting LIRB4 or ILT3. And you can see their application in multiple tumors, multiple types of solid tumors, as well as in leukemia, hematologic cancers. And IO-106 is ready for IND-enabling studies. I'm very pleased to be invited by Judy and the Myeloid Network group to give the talk. We appreciate all the groundbreaking work done in the myeloid biology, and we are also proud to be able to translate the expert knowledge in myeloid biology and immuno-oncology collectively with our academic collaborators and immune scientists. We therefore build a highly differentiated and growing pipeline with our expert team to advance the pipeline and demonstrating benefits of targeting myeloid checkpoints for cancer patients. So I really am happy where we are and happy to answer your questions.
Well, thank you very much for a great talk. It's really exciting to see all these developments. So we have a couple of quick questions, and then we are supposed to take a break, so we can continue talking into the break if people have time. So first of all, a question from Kamal Puri. What are your thoughts on the contribution of LILRB1 in addition to LILRB2 in immune suppression? And would it be better to target both?
I think LILRB1 and LILRB2, they are different. First of all, LILRB1 is expressed in more cell types than LILRB2. It is also expressed on lymphoid cells, natural killer cells, for example. And additionally, they do have different sets of ligands, although they have a shared ligand, which is class 1 MHC, as well as, particularly HLA-G. But we believe LILRB2 is a primary myeloid cell focused checkpoint, and there is an advantage to target LILRB2 by blocking all ligands from binding to LILRB2. That is what our antibody is able to do. If you try to do a dual targeting antibody, you may be able to block HLA-G, but we don't know if there could be other unintended consequences in safety or space for other immune inhibitory ligands to still go through signaling. So we think based on the mechanism of action, you really need to saturate the immune inhibitory receptor of your choice, and in this case, LILRB2. And we have seen, as well as Merck, each of us has a unique LILRB2 specific antibody. We all have seen clinical benefits.
Okay, thank you. So we're running 10 minutes behind, and to try to keep to schedule for our last speakers, why don't we take a 10-minute break, and then if anybody wants to continue asking questions of Charlene during the break, I think that'd be okay. Otherwise, please answer the questions in the chat, and hopefully these talks will spark more interactions with people. So feel free to take a 10-minute break and come back at about 11:50 Pacific time, 2:50 Eastern time.
Thank you. Thanks, Judy.
Thanks.
Yeah, I think we can get started in a minute or so.
Yeah, I think so. All right. Oh, always do that.
Okay, so I think in the interest of time, we can get started. Welcome back. This has been a fantastic day of science, and I think the third session will be just as exciting. So the next speaker is Dr. Hannah Garner. She's a postdoctoral fellow in Dr. Karen de Visser's lab in the Division of Tumor Biology and Immunology at the Netherlands Cancer Institute. Hannah, do you want to go ahead and put your slides up? Hannah's going to be talking to us today about understanding how breast tumors hijack myelopoiesis to promote immunosuppression and disease progression.
Great, can you see my slides?
We can.
Great, thank you so much for the introduction, and I would like to take the opportunity to thank the organizers for inviting me to speak today. It's really my pleasure to be here to tell you about my work, understanding how breast tumors hijack myelopoiesis to promote immunosuppression. So breast cancer may not be what you immediately think of when you think of a systemic inflammatory disease, but actually what we know is that solid tumors, including mammary tumors, can produce all kinds of pro-inflammatory mediators, such as cytokines, chemokines, and growth factors, which act not only on the local tumor microenvironment, but can also impact distant tissues, including, and of particular interest to me, the hematopoietic system. And this can skew the hematopoietic output and the composition of the blood, which in turn skews the composition of immune cells at distant tissues. And this can have a profound impact on whether or not a tissue is permissive to metastatic outgrowth or not. And in Karen's lab, we're particularly interested to understand how myeloid cells impact anti-tumor immunity. And of course, the myeloid system is highly heterogeneous. There's lots of different, very distinct cell types. And some of these cell types can positively impact anti-tumor immunity. For example, we recently showed that eosinophils are critical for response to immune checkpoint blockade in breast cancer patients. But I'm not going to talk about this in much more detail today. Karen recently presented this work at the Myeloid Network, but really just to use this as an example of how myeloid cell type can really have a positive impact on anti-tumor immunity. Today, I want to talk more about neutrophils, which have been shown in many preclinical studies to mechanistically promote disease progression and metastatic spread, and in clinical observations have also correlate with increased disease progression. So this is immunophenotyping data from patients with advanced triple negative breast cancer. And what you can see is that patients with advanced disease have increased neutrophils in the circulation. And not only are the neutrophils increased in breast cancer patients, but they are also producing more nitric oxide, suggesting that they are functionally different in breast cancer patients. And this closely mirrors what we've previously seen in a spontaneous mouse model of mammary tumorigenesis, where we see that mammary tumors produce considerable amounts of IL-1 beta. And this IL-1 beta kickstarts a whole pro-inflammatory cascade that leads to systemic neutrophil expansion and polarization. And this neutrophil polarization is again typified by increased nitric oxide production, which can suppress cytotoxic T cell functionality and leads to increased metastasis. We know that if we get rid of neutrophils in this model, we get significantly less metastasis. And what I wanted to understand with this project is really how and when neutrophils become tumor educated. So at what point during a neutrophil's lifespan do they become imprinted with this immunosuppressive phenotype? And can we identify clinically relevant anti-inflammatory treatments that can reverse tumor-induced neutrophil education? So we can't get rid of neutrophils in patients like we can in the mice because they're so important for our response against opportunistic infections, but can we reprogram them to be beneficial to patients? Before I go any further, I just want to introduce this schematic of a hematopoietic tree with the caveat that this is a highly simplified and classical hematopoietic tree, but it does illustrate that at the top of the tree, we have long-term hematopoietic stem cells, which can give rise to all circulating blood cells through a series of progressively restrictive differentiation steps. And as I mentioned before, the hematopoietic system is highly dynamic and can rapidly integrate systemic cues and switch its production, particularly towards the myeloid lineage, in a process which is known as emergency hematopoiesis or emergency granulopoiesis. And this has principally been studied in the context of acute inflammatory situations, but it's less clear how the transcriptional control of lineage determination is altered in chronic inflammatory situations, such as breast cancer. So what we wanted to really understand is whether in tumor-bearing hosts, neutrophils undergo multiple layers of education, whether changes in hematopoiesis as a result of chronic inflammation really form the basal layer of education, which is then built upon as neutrophils undergo tissue specification in tumor-bearing hosts. So just before I dive right into the data, I want to introduce to you the mouse model that we use. We call it the KEP mouse model. And these mice have CRE under the control of keratin 14 and E-cadherin and P53 flocks, and they develop spontaneous mammary tumors at around 6 to 8 months of age. And I've been characterizing the hematopoietic stem and progenitor compartment all along the neutrophil development trajectory. And what we can see when we compare the hematopoietic stem and progenitor cells in terms of frequency in tumor-bearing mice compared to age-matched wild-type mice, we can see increases in a number of these populations along the neutrophil development trajectory. And this is that we see the same trend when we look at absolute cell counts. To understand what is going on in a bit more detail, we isolated 7 populations along the neutrophil development trajectory from long-term hematopoietic stem cells all the way through to mature bone marrow neutrophils. And we performed RNA sequencing and attack sequencing on these populations. Now, in the interest of time, I'm only going to talk about the RNA sequencing today, but just want to mention that the ATAC sequencing really supports and confirms the conclusions that we draw from the RNA sequencing. And this is an overview of all the differentially expressed genes. You can see that in all the populations that we looked at, we see a number of differentially expressed genes in tumor-bearing mice compared to wild-type mice. And when we perform a principal component analysis, looking at all genes, not only the differentially expressed genes, what we see, and it's actually easier to see if I zoom in on the hematopoietic stem and progenitor part of the PCA, is that the progenitors from tumor-bearing mice are always one step closer to the next step in the development trajectory of wild-type mice. So for example, here, what you can see in the red triangle is a multipotent progenitor from a tumor-bearing mouse, and that is actually closer to the common myeloid progenitor of a wild-type mouse than it is to the multipotent progenitor of a wild-type mouse. And again, we see the same thing here, where the common myeloid progenitor of a tumor-bearing mouse is more similar to the granulocyte monocyte progenitor of a wild-type mouse than it is to the common myeloid progenitor of a wild-type mouse. So this suggests that neutrophils, that hematopoietic stem and progenitor cells are accelerating in terms of differentiation in tumor-bearing mice. And when we zoom into the common myeloid progenitor in a bit more detail, and I performed gene set enrichment analysis on all the populations, but just to focus on the common myeloid progenitor, you can already see that these cells are enriched for neutrophil-specific genes, and the common myeloid progenitor actually shouldn't, in terms of classical wild-type or steady-state mice, shouldn't be committed to the neutrophil lineage yet. So what we think is happening is that in tumor-bearing mice, neutrophil differentiation is accelerated. When we look at the bone marrow neutrophils, what we can see is that immature neutrophils are actually the most expanded population in the bone marrow of tumor-bearing mice, taking up to around 40% of all bone marrow cells. And not only are these cells massively expanded, but they're also highly enriched for an immunosuppressive gene signature. We actually see this gene signature also in the pre-neutrophils and in mature neutrophils, but it's most strongly expressed in the immature neutrophils, which also happen to be the most expanded population in tumor-bearing mice. And I'm in the process of trying to understand which transcription factors actually control this immunosuppressive gene signature in tumor-bearing mice. But to summarize, what we can see so far is that mammary tumors accelerate commitment to the neutrophil lineage and induce an immunosuppressive gene signature in immature bone marrow cells. So I told you at the beginning that in this model, mammary tumor-derived IL-1 beta kickstarts the whole inflammatory cascade. So then my question was, what happens if we treat with anti-IL-1 beta? And in the blood, we see that treatment with anti-IL-1 beta reduces neutrophil expansion. That's the red line compared to the blue line. And it also reduces the appearance of c-KIT positive neutrophils in the blood. Again, the red line compared to the blue line. When we look at in the bone marrow at the same 7 populations, again, we begin to see a normalization of these expanded populations. So at the cellular level, treatment with anti-IL-1 beta is beginning to normalize hematopoiesis and blood neutrophils. But what happens at a transcriptional level? So again, this is on the left here is an overview of all the differentially expressed genes in tumor-bearing hematopoietic stem and progenitor cells from tumor-bearing mice compared to wild-type mice. And then on the right here, we have the same genes when we compare tumor-bearing mice treated with anti-IL-1 beta to wild-type mice. And you can see that these genes are no longer upregulated or significantly upregulated or downregulated. And it's perhaps easier to see if I zoom in particularly to the common myeloid progenitor again. So here in red, we have the genes that are downregulated in tumor-bearing mice compared to wild-type. And you can see that in yellow, in tumor-bearing mice treated with anti-IL-1 beta, this is restored, they are upregulated again. And again, the same thing here in terms of genes that are upregulated in tumor-bearing mice compared to wild-type are then downregulated again in tumor-bearing mice treated with anti-IL-1 beta. So finally, does this have any impact on metastasis and disease progression? So to understand this, we use an orthotopic transplantation model. So we take tumor fragments from the kept mice, we orthotopically transplant them into the mammary fat pad of wild-type mice, and then let these grow out. We can perform mastectomy and then wait for these mice to get clinically overt metastatic disease. So we treated these mice with either isotype control antibody or anti-IL-1 beta before mastectomy, so in a neoadjuvant setting. And what we can see is that we see reduced metastasis, both in the lungs and also in terms of lymph node metastasis in mice treated with anti-IL-1 beta. And this is very preliminary, but we begin to see a trend towards potentially reduced neutrophil superoxide production in mice treated with anti-IL-1 beta compared to control-treated mice. So with that, I would like to summarize what we see in this model is that mammary tumors have a profound effect on the hematopoietic system, which I still find really amazing that, you know, we have a distant mammary tumor and it can have a really dramatic effect on stem cells in the bone marrow and hematopoietic output. And we can normalize this with anti-IL-1 beta treatment, and anti-IL-1 beta treatment also reduces metastasis formation. And with that, I would like to particularly thank my amazing postdoc advisor, Karen de Visser, and the whole of the de Visser lab. And I particularly would like to mention the group of Elzo de Wit, particularly Ningqing and Marino, who've been really instrumental in helping me with the ATAC-seq and RNA-seq analysis. And I thank you for listening.
Thanks so much, Hannah. So there's a couple of questions in the chat and we have a few minutes. So maybe I'll ask the first one. So when you use the anti-IL-1 beta and there's normalization of hematopoiesis, is there other changes besides the neutrophils?
So actually so in the stem and progenitor cells, yes. That we also see a kind of normalization. So monocytes are also increased in this model, and we begin to see a normalization in monocyte cell numbers, but we haven't done the RNA sequencing. So I don't know if transcriptionally they are also normalized. But what's really interesting is that particularly in the wild type mice treated with anti-IL-1 beta, we see that there is a skewing towards erythropoiesis, and IL-1 beta actually controls the lineage decision as to whether you go towards neutrophils, monocytes, or whether you go towards erythropoiesis. So there is also the potential that treating with anti-IL-1 beta can normalize erythropoiesis in tumor-bearing hosts, which is something that we're looking at because, of course, a disease-induced anemia is also a problem for patients.
Okay, very interesting. Dimitri asks about, he says acute infection after initial mobilization of neutrophils from bone marrow is associated with strong myelopoiesis and production of immature neutrophils. Is this trajectory similar to that observed in cancer? Is this shift in trajectory enough to generate immune suppressive cells?
So what I think is let me just, is being asked is whether it's the same in acute inflammatory situation to a chronic inflammatory situation. I don't know exactly whether at a transcriptional level it's exactly the same, but it certainly seems to be a similar phenotype where we also see this massive expansion of immature neutrophils, and that seems similar.
There's one more from Jashodeep Datta, which he asks, in which cells in this model is the inflammasome most activated? You might suspect innate immune cells would have the strongest inflammasome-induced IL-1 beta. Did you show that neutrophils in your model express IL-1 receptor 1? And did you see alternate fate trajectory in circulation versus tumor in this model with and without the IL-1 beta inhibitor? If you could just maybe answer in like 1 or 2 sentences, and then it'd be the rest of the chat.
I think it's easiest just to say that neutrophils in this model do not express the IL-1 receptor particularly highly. Neutrophils predominantly express the decoy receptor. And actually in the cells that we sequenced, it's hematopoietic stem and progenitor cells that really express the highest amounts of IL-1 receptor 1.
Great.
And I can answer more questions in the chat.
Awesome. Thank you so much, Hannah. Okay, so our next speaker is Dr. William Hill. He is a postdoctoral fellow in the Swanton Lab in Cancer Evolution and Genome Instability Laboratory at the Francis Crick Institute in London. And William, if you want to put your slide up, his title today is Lung Adenocarcinoma Promotion by Air Pollutants. I'm very excited to see this talk. William, I'll hand it over to you. Thanks so much.
Thanks for the opportunity to talk today. And it's nice to follow one IL-1 beta story with another. So yeah, I'm going to talk today about our study into air pollution and lung adenocarcinoma. And I think when we think about how environmental carcinogens cause cancer, there's a very classical model typified by UV light and tobacco, which directly induce mutations. And it logically follows that the more mutations that you have an elevated risk of tumor formation. But there's I think quite a few other considerations that this model requires. For example, the BRAF V600E in melanoma is not actually within the UV mutational spectrum. We know from Sanger and a range of other studies that normal healthy tissue harbors these oncogenic driver mutations, and these accumulate over time, but don't seem to form frank tumorigenesis. And in mouse models treated with a range of environmental IARC class 1 carcinogens, they were sufficient to drive tumorigenesis without actually elevating mutation burden or inducing specific trinucleotide mutation or context changes. And even in our study, where we sequenced lung tumors from people who have smoked, in around 10% of cases, these patients do not have driver mutations driven by tobacco. So what's happening? So there's another model proposed almost 76 years ago now, where they broke tumor initiation down into 2 steps. There's an initiator step induced by DMBA, which causes the mutation, and a second promoter step, which causes clonal outgrowth and acts as selection pressure on these mutant clones. And so we wondered whether air pollution, which is not known to induce a specific mutational burden, might be acting by this promotion model. And the reason we decided to focus on lung cancer specifically in people who had never smoked, because a recent study where they carried out whole genome sequencing of over 200 patients with lung cancer who have never smoked actually found that the vast majority of the mutations could not be attributed to an exogenous mutational signature, suggesting that exogenous risk factors are acting in a non-mutagenic fashion. And so we took a 3-pronged approach to investigate this. We investigated the geographical relationship between EGFR mutant lung cancer, which is highly common in people who have never smoked, and levels of PM2.5. We developed mouse models in the lab where we induce oncogenic expression, the EGFR oncogenic driver mutation combined with administration of particulate matter to functionally understand this. And finally, for this model to hold, it would require that these EGFR driver mutations are present in histologically normal lung tissue. And so we explored that using two ultra deep sequencing profiling techniques. And so I'm just going to focus on number 2 and 3 today in the interest of time. But just to say, for the epidemiology and epidemiological analysis, we did see a significant association between the incidence of EGFR mutant lung cancer in these 3 different international cohorts in the UK, in South Korea, and Taiwan, was associated with annual mean levels of PM2.5, suggesting there is this association between EGFR mutant lung cancer and air pollution. And when I say PM2.5, what I'm referring to is particulate matter less than 2.5 microns, which is a key component of air pollution. And so to model this in the mouse, what we did was we can induce the oncogenic driver on day 0, and then we give intratracheal administration of particulate matter 3 times a week for 3 weeks, and then we just analyzed tumor formation at 10 weeks post-induction. And in these 2 EGFR models, what we found is that in both models, exposure to particulate matter was sufficient to significantly elevate and promote tumor formation. In the model on the left, what we found is that there was an increase in these small pre-neoplastic lesions. And in the more aggressive CCSP doxycycline model on the right, what we found is that there was an increased number of these adenocarcinoma foci per mouse. And so it looks like that we've developed a model whereby we can study how particulate matter might be promoting lung tumorigenesis in the mouse. And just as a kind of confirmation, what we did was we carried out whole genome sequencing of these tumors, both from control treated or the air pollutant exposed mice. And we saw no significant increase in the number of mutations in the polluted sample, no specific enrichment for any mutational signature, SBS signature, and no specific enrichment of DNA-based changes, be it C to T, T to A. And so what we then thought was, what are the inflammatory changes that are being induced by pollution which might be promoting this? And we also wanted to look at what the effects on the epithelia were. And so what we did was we carried out this organoid forming efficiency assay as a measure of stemness within the epithelial compartment. So what we did was we induced the EGFR mutation, gave it the 3 weeks of exposure, and then we harvested them, and you plate 10,000 sorted epithelial cells in this co-culture system, and you can count the number of organoids that form as a readout of the progenitor-like ability of these cells. And when we did this, we actually got quite an interesting result. It turns out that in the normal epithelia, in the naive mouse exposed to pollution, there was no significant change in the organoid forming efficiency. Expressing EGFR mutation in the epithelium had little impact on the organoid forming efficiency. And it was only when you had the combination of expression of the oncogenic EGFR driver and exposure to the air pollution that this led to a significant increase in the organoid forming efficiency. And so what we think is that neither of these are alone, but together they seem to be sufficient to induce this progenitor cell state. And so we wanted to explore how this might be happening. And so we carried out both FACS analysis of the different immune populations, and I'm just showing some of the fluorescent imaging here. And what we found is that macrophages seem to be a key responder to particulate matter in the lung, unsurprisingly. And what we found is that acutely on the left-hand side, directly after 3 weeks of exposure to the particulate matter, the number of these macrophages increased. But even at 10 weeks post-induction, this is almost 2 months past we've stopped exposure to particulate matter, there seems to be a sustained and still significant elevation in the number of macrophages that are present. And you can see here, they really surround the lesions that form. And so to test the functional requirement of a competent immune system, Eva did some amazing work crossing our genetically engineered mouse model onto the Ragnall IL-2 receptor gamma null system. So this is deficient in T cells, B cells, lacks NK cells, and also the myeloid compartment will be disrupted. And so when we repeat the same experiment in this model, we actually find that particulate matter no longer increases the number of these early neoplastic lesions that form in the mouse, suggesting that a competent immune system is required for these particulate matter, particular PM-mediated tumorigenesis. And so then to dig down into what might be the signal that's coming from the immune system that's promoting the tumorigenesis, we were very intrigued by this study that came out several years ago now, where they took patients at elevated risk of cardiovascular disease and gave them canakinumab. And as a kind of secondary endpoint, what they found was that there was this dose-dependent decrease in the incidence of new lung cancer cases. And so it's known that R1 beta is sufficient to induce and elevate the organoid forming efficiency of these of the lung epithelium. It's known that PM2.5 delivery into the epithelium and macrophages can elevate R1 beta release. And so we really wondered whether R1 beta might be the signal driving this effect. And so what we did was we just confirmed where the primary source of the R1 beta was. So we carried out RNA scope. And here you can see a really nice co-localization between the CD68 staining and the R1 beta RNA. So we find that particulate matter exposure elevates the number of positive cells, and also that the vast majority of these cells are CD68 positive. And so then to kind of functionally test whether the macrophages are sufficient to alter the cellular state of the epithelia, what we did was we exposed mice to air pollution, and we harvested the macrophages from these PM exposed mice. And then we took EGFR mutant epithelial cells from mice that had never seen pollution, and we could then repeat the co-culture assay to test whether PM exposed macrophages are sufficient to elevate the organoid forming efficiency and alter the cell state of these EGFR mutant cells. And super interestingly, when we did that co-culture, we looked at both the interstitial macrophages and the alveolar macrophages, and polluted both macrophage lineages were sufficient to elevate the organoid forming efficiency of EGFR mutant epithelial cells. And so I think what this highlights is how that the macrophages are secreting a signal which is inducing the cellular reprogramming of the EGFR mutant cells. And then finally, to test the requirement of R1 beta in vivo, we administered the R1 beta, the anti-R1 beta only during the 3-week exposure to particulate matter. And then at 10 weeks post-induction, we again looked at the number of adenocarcinoma that formed, and we found that there was a significant attenuation of tumor formation in these mice, really suggesting that we think that R1 beta is a key signal in this process. And so then, just in the last minute or so, it must, to fit with the promoter model, it must be that these pre-existing EGFR mutations are lying dormant within lungs. And so we took 3 clinical cohorts of almost 300 normal tissue samples, and we carried out ultra deep sequencing for the EGFR oncogenic driver mutations. And we found them in about 18 to 20% of samples harbored an EGFR activating driver mutation. And then what we did is, because we had a large clinical cohort, we actually took a measurement of anthracosis, which is black pigmentation in the lung H&E here, you can see on the left. And this is associated with exposure to environmental pollution. And what we found was that just the binary presence or absence of this was not associated with the mutation, but it actually increased and drove expansion of these EGFR mutant cells. And so what we think is happening is that IL-1 beta secreted from the immune system in response to particulate matter is acting on these occult EGFR mutant cells that arise over time, and that this is driving cellular reprogramming, which is driving the initiating event in lung adenocarcinoma. And so I'd just like to thank everyone for listening and the huge amount of teamwork that went into getting this work achieved. And I'm happy to take any questions.
Thanks so much, William. That was very interesting. I'm trying to sort through the chat questions. It's a little difficult to see who they're for. If you have questions for William, maybe you could just say William and then the question. But William, I'll start with a question. So, and sorry if I missed this, is this specific to the tumor cell intrinsic mutation? Or do you think that, for example, like lung metastasis from like a breast tumor is worse when there's the particulate matter?
Yeah, that's a really great question. I think there was some very long time ago, maybe about like 50 years ago, and they did, I think there was some evidence that exposure to particulate matter could elevate metastasis to the lung. So it does seem to be both primary and secondary tumor formation.
Okay. Judy, do you have a question for William?
Yeah, I'd like to ask a question. IL-1 beta is a really good recruiting factor for bone marrow derived myeloid cells. So do you think there's the IL-1 beta is coming from the alveolar macrophages, and then could it possibly also be enhancing inflammation by recruiting other immune cells that are doing damage? Or
Yeah, definitely. I think that IL-1 beta is going to have a numerous number of roles in our system, and I think it would be important to pick apart the effects on the immune system of IL-1 beta versus the effect on the epithelia. But I think it's super interesting to see that this interaction of the immune system and the specifically the mutant epithelia in this study.
I just from you've done these beautiful studies. Have you looked at whether there's an increase in IL-1 beta in, say, numerous patient samples that have anthracosis? I'm not sure whether you showed.
Yeah, we haven't actually looked at IL-1 beta in patients. I know there's a number of studies where they've taken blood from people who live at high levels of particulate matter, and I think there's some evidence that inflammatory markers are elevated. One of the other interesting findings is that we've looked in the normal tissue of normal lung tissue, and we did some immune profiling just by multiplexed imaging, and we did find that actually macrophages seem to positively associate with the levels of particulate matter that people were exposed to. So there does seem to be an increase in macrophages in people who live at high levels of air pollution.
Thank you.
Great. Thanks so much, William. If there's additional questions, I'm sure William would be happy to answer them in the chat. Okay, so our last speaker of our annual symposium is Dr. Sofia de Oliveira, who is an assistant professor in the Department of Developmental and Molecular Biology at Albert Einstein College of Medicine. And the presentation will be Meta-Inflammation Impacts Neutrophil Biology, Lessons from the Zebrafish. And I will turn it over to you. Thanks so much.
Hi, can you hear me?
Yes.
Yes, hi. Thank you so much for allowing me to be part of this amazing, tremendous day of amazing research. It's really nice to be here representing the zebrafish, bringing some work that we've been developing on neutrophils. So I like to think that we have come a long way since Elie Metchnikoff, the father of cellular immunity, discovered the phagocytes and described the neutrophils for the first time. So I think we also came a long way since David Rogers in Vanderbilt was looking at neutrophils migration into a dish. And we can really, we've been really good in the last decades in accomplishing tremendous knowledge in the neutrophil field, in part also by introducing new models that allows us to use a to look at these fragile innate immune cell that is so reactive, such as the neutrophils. The zebrafish has really been playing a huge role, and nowadays we can really be looking to these amazing cell and how they behave and manipulate it in the system. The zebrafish has brought to us this capacity to visualize and to manipulate neutrophils, but also importantly to look at these cells at the whole animal scale. And in the lab, we've been developing unique skills that allows us to look at the neutrophils migration at the whole animal context, for example, towards a wound. And these fish are fish with 2 weeks old, for example, already with an adaptive and an innate immune system present. We are able not just to do these visualization at the whole animal scale, but we can zoom in and go and see, for example, how neutrophils are involved in the development of, for example, liver disease, since we can really image through non-invasive microscopy the organs such as the liver. And I hope you can appreciate how beautiful it is to be able to see these cell interactions into a tissue in an organ, but also, we can also look at these in the cancer context, where we can look at how neutrophils and macrophages are interacting together to fight against these malignant keratinocytes, or by injecting human or mouse cell lines, cancer cell lines, and we can really get the power of doing long-term imaging up to 72 hours. So the zebrafish, as some of you might know, I really like to see it as a unique model to study the neutrophils. Transparency is, of course, in the front line of the advantages, but also the high fecundity, the small size that allows us to have thousands of fish in our facilities. But also none of these would be really important if not because it's really easy to genetically manipulate the zebrafish, but also the remarkable genetic similarity it has with humans, with about 70% of homology. And also it's a diurnal animal, which has, in the neutrophil scenario that we know it's regulated by circadian clock, is actually a good factor for the type of research we've been doing. So we've been publishing quite a few papers in the field in the last about 12 years. So what we learn, or what I learned through my path in the zebrafish and neutrophil biology, is that we kind of know a lot about how neutrophils establish, or how neutrophils are regulated in terms of maturation, production. We've been learning quite a lot of that. We've been learning quite a lot about the cascades that are involved on the neutrophil recruitment to an injury, to a trauma, infection, and cancer. What it's a little bit less clear is how neutrophils and how this traditional neutrophil response is actually changed or impacted by the presence of meta-inflammation, which is a low grade of systemic inflammation that is associated to metabolic dysfunction. So really, when I started my lab at Einstein during the COVID pandemic, I really wanted to focus on these questions and investigate the impact of meta-inflammation and also inflammaging on the neutrophil biology, and how such modifications could alter this traditional neutrophil response in different contexts, such as trauma, infection, and cancer. So we built this obesity, diabetes, and metabolic syndrome are really like a silent epidemics. We know that neutrophils are really involved in the development of, for example, non-alcoholic fatty liver disease and other obesity-related diseases. There's a lot of literature that shows some changes in different features of the neutrophil biology, maturation, activation, cytokine release, and ROS production, for example, and mitosis. But really, it's kind of controversial to feel right now. And with these incredible function of neutrophils that are right now much more than microbe killers, and we know they have a tremendous impact on inflammation, regulating other leukocytes by their cell heterogeneity, but also cross-talking with many other immune cells and being active players on the onset of inflammation, but also on the resolution of inflammation. It became quite clear that we're just touching the tip of the iceberg, and we really need to understand better how meta-inflammation is impacting behavior, heterogeneity, proteome secretome, and many other aspects of the neutrophil biology in homeostasis and in the disease. So while we're trying to fill the gap with our model, we decided to use the zebrafish diet-induced non-alcoholic fatty liver disease model that I started to characterized and used during my postdoc studies at the Hutton Locker Lab at UW-Madison. And this system consists on feeding and giving and providing the fish with a high cholesterol diet. But right now in the lab, we are working, and we already have other diets. We're trying to establish reference diets in the zebrafish field that will allow different researchers to use Western diets and high-fat, high cholesterol diets to really understand how meta-inflammation is impacting different aspects of biology. So using this model, our first question was, can we use this model to study how the meta-inflammation or how the metabolic syndrome is impacting the neutrophil response towards additional injuries? So the first thing we did was to run a panel of gene expression, so qPCR of the whole fish, just to try to understand if we saw some kind of metabolic and inflammatory response. So we indeed observed that there is an increase on the expression of inflammatory genes such as IL-1, IL-6, IL-8, which zebrafish has IL-8 contrary to the mouse model. We could also see that metabolic dysregulation is occurring. We have an increase of GLU2 and insulin. And so it really seems that these non-alcoholic fatty liver disease larvae are developing meta-inflammation. Which was really nice to see is when we took our fish to under the scope. So instead of just looking to the liver, we started to look systemically into the whole larvae. And it was quite clear that in a normal condition, normal fish where the neutrophils align in the caudal hematopoietic tissue and kidney, which are the primary hematopoietic organs at this stage, 2-week stage. Really, when we look at the fish with non-alcoholic fatty liver disease, we have these tremendous systemic inflammation, recruitment, we have infiltration of neutrophils and macrophages into different tissues. And when we start to look and analyze these, we really start to see like an infiltration of neutrophils into the skin, the muscle, intestine and liver, into the heart and into the brain. So when we measure that, we saw that around 80% of our larvae are actually with a severe type of systemic inflammation, and 20% are developing a mild moderate phenotype. What really was also apparent to us is that we have an increased production of neutrophils and macrophages. We have 1.3 more neutrophils in these larvae and 1.8 more macrophages. We used EDU to look at proliferation in the full fish. We indeed have an increase of proliferation in the whole larvae. We also have an increase of proliferation on the hematopoietic tissues, such as the CHT and the kidney, which suggested to us that we are getting an emergency myelopoiesis occurring by the consumption of these Western type diet. Another thing that we looked was the hematopoietic stem cells, and we also saw that these NAFLD larvae have an increased number of HSPCs. We looked at these by microscopy, where we quantify the total number of CD4.1, but we also use flow cytometry to quantify the number of RUNX1 and Cherry positive cells in these whole larvae. And in both of them, we saw an increase of HSPCs. But how is these meta-inflammation impacting the neutrophil response? So for us, the easiest way is really just to perform a tail fin amputation on these fish that they've been consuming this Western type diet. And it was extremely surprising for us to see this exacerbated neutrophil recruitment that we're seeing to a simple injury in the skin with a huge and massive recruitment of neutrophils. When we start to look a little bit more into depth, like into how are these neutrophils being impacted, we saw a tremendous change in the neutrophil recruitment. So it's exacerbated, but also the peaks of the recruitment are delayed. So usually we have a peak around 4 hours. Now we're having a peak around 6 hours into the recruitment to these injury. And when we looked at the resolution 24 hours after the injury, we have a significant reduction of the neutrophils into these injuries. However, such is not occurring in the larvae with non-alcoholic fatty liver disease. When we looked at the ROS production, we also observed that the neutrophils at the wound that were exposed to these Western type diet are actually producing higher amounts of reactive oxygen species. Other thing that we looked was using our transgenic lines that they have nuclear, but also cytoplasmic markers. We looked at netosis in vivo, and in the many movies that we could look from our controls, we barely, or we could almost never detect neutrophils undergoing netosis, which means like expelling pieces of their nucleus together with the cytoplasmic material. But indeed, we could see these events occurring quite often in our NAFLD larvae. And this is just a movie to show you how this looks like in vivo in our zebrafish model, where we really see these extrusion of nuclear content together with cytoplasmic content with neutrophils that are continuing to be alive and moving around for quite a long, and then eventually we see them dying. Other thing that was quite clear to us was that neutrophils seems to be moving quite differently. So we measured the neutrophil velocity, and we saw that the neutrophil speed is increased on NAFLD larvae. So this is seems not to be just present on the meta-inflammation. We have other models of chronic inflammation, such as, for example, the skin chronic inflammation model that a student came from Victor Molero's lab, my PhD mentor from Murcia. He got this model that has a skin chronic inflammation, and when he measured, he also observed that there is an increase of speed on these neutrophils compared, for example, to a condition that we rescue these recruitment to the skin. We performed some behavior analysis that now we're trying to use also to compare to perform in our meta-inflammation model to really try to, and he observed that we are being able to use the zebrafish in our videos in collaboration with Hidalgo's lab, that they're being tremendous in helping us on bringing these to the fish. We are being able to identify different clusters that align very well with different conditions, and we are eager now to bring these to our meta-inflammation systems and the other ones that we have in the lab. So one thing that we wanted to, just finishing my talk, we knew that neutrophils can be recruited from different inflamed areas, and they can, respond to injury. So neutrophil reverse migration has been discovered first time, in the zebrafish. And we know that these neutrophils that can really reverse migrate from a wound, and they can go to other tissues. That has been also shown in mammalian systems by Paul Cube's lab. So we knew neutrophils can infiltrate the liver in NAFLD larvae, as you can see in here. So we asked the question, so if we photoconvert the neutrophils in this liver area, can these neutrophils be recruited to are they being primed and later on being recruited to this injury? So in these, we performed this experiment. We photoconverted the neutrophils in the liver and posterior intestine area, and we have observed that 50% or more than 50% of the neutrophils that are being recruited to an injury in an FLD larvae, they are actually coming from that area, which kind of shows that neutrophils are being primed at these areas, and then they're able to reverse migrate to secondary stimulus. So, but can we treat or rescue these with drugs that could treat NAFLD? So we have a few drugs that we knew in the lab that they are able to rescue steatosis. So metformin used in diabetes patients, but also pentoxifylline, a TNF-alpha inhibitor, secretion inhibitor. So we treat the fish after they already developed NAFLD. So we treat them for 3 days with these drugs, and actually could see that treatment of these drugs can rescue the systemic inflammation in these fish. And later on, it can actually rescue also the exacerbated recruitment that we observed previously. So I hope our work can really show us how we can use the fish to study meta-inflammation impact on neutrophils. And we are now really trying to explore how meta-inflammation is impacting neutrophil biology in polytrauma, in the development of liver disease, and also in cancer. So thank you so much. And I would like to thank my lab that joined me in this last 2 years. It's growing, and all the supporting that we're having from different collaborators and from the community. Thank you so much.
Thanks so much, Sophia. Those images are so beautiful.
Thank you.
Feel free to put some questions in chat or turn on your video. So Sophia, maybe I missed this, but what is the Western diet doing? Is there some sort of metabolic regulation?
We have different ones. So this one that I showed today is about a high cholesterol diet. So we are seeing that is inducing a non-alcoholic fatty liver disease, actually steatohepatitis. We have done proteomics, qPCR. We are undergoing single cell RNA-seq also in the fish. but definitely there is a metabolic dysregulation. We're not the only ones using these. We are the only ones using these at this stage for this purpose of studying neutrophil response, but it's an established protocol that many labs have used that they see with time, the fish develop obesity, they develop diabetes and insulin resistance. And now we're just creating reference diets so that the field can go and start using it similar to they do in mice.
But could it be the lipids that are regulating the neutrophil phenotype?
It also could. So these are our questions. So one experiment I think that is key to understand this, the impact on the neutrophil versus the impact on the system, right? The cell autonomous effect is actually transplanting these neutrophils now to fish that they have never been exposed to the diet and do again the injury and see if when we compare them with normal neutrophils never also exposed to having the same animal neutrophils from an older animal, but also a new animal without being exposed to the diet and try to see if they respond differently. So this is a key experiment for us to kind of like, separate these two things in the system, but it's possible. And I think it's both.
There's a question in the chat saying that the behavior clustering is super interesting. Do you think we can single cell profile photo-converted neutrophils?
Yes, definitely. So this is where we're moving now. So we're just very new. We're really happy. And I wanted to show the how I think amazing this efficient model is going to be to look at the neutrophil behavior analysis that are starting to come out. Hidalgo was amazing on bringing these at the last year. So instead of just looking at 2 hours of movies, if you think about, we're looking to 24 hours, even 72 hours of behavior. So now we have all these questions in our head if we can identify pathogenic behaviors in different types. We have infection, we have meta-inflammation, liver disease, and cancer, and polytraumatic injury, that we can start to compare and use the capacity of imaging the neutrophils non-invasively and start to understand how the cell are changing the behavior morphology, but even the nucleus, because we have nuclear markers and cytoplasmic markers. So it's been really interesting, and we want to, now we kind of need some help in the future is to try to align these behaviors with transcriptomic profiles and proteomic profiles that we don't have any expertise on that. And so that is where we're going to move next. But it's been a tremendous, effort.
I'll ask just one more question from the chat and then I'll close the session. So Jashodeep Datta asks if this could explain why the NAFLD liver makes it more hospitable for metastasis from GI tumors.
Yes.
Are there reverse migrated neutrophils have different behavior when they infiltrate other?
Exactly. So these are part of the questions that we're actually trying to understand. For example, in the grant that we won, a MIRA grant last summer, we are actually trying to understand how the meta-inflammation, the presence of NAFLD, metabolic syndrome, because our fish, they are not obese yet. We are studying a model that is a pre-obesity, pre-diabetic. So, and we're already seeing a tremendous impact. So we won a grant from NIH, MIRA, to understand how meta-inflammation is changing prioritization mechanisms of neutrophils to polytraumatic injury, and how neutrophil reverse migration can actually be another way that is contributing with neutrophils that enter the circulation that could take inflammation or being reprogrammed in the tissues and taking inflammation to other organs. Like we associate most of the issues that occur with neutrophil biology to maturation problems, where the system is throwing thousands of neutrophils immature that are dysfunctional, but neutrophil reverse migration can actually probably playing a role, and our model is going to be great to address these questions. So
great. Well, thank you.
Thank you so
do you
much.
have a question, or should I close the session?
I think we should wrap it up. And,
yeah, okay. Sounds good.
Yeah.
So just on behalf of all of the organizers, I would like to thank the speakers and the attendees for just such a fantastic symposium, and also to thank all the members of the Myeloid Network. None of this is possible without your monthly participation, and coming together every month to share science is really what's going to drive this field forward to help patients. We'd also like to thank the UC San Diego Moores Cancer Center and Adam Prater for both hosting the Myeloid Network and also the symposium, and to AstraZeneca for their generous support to financially support the program. As a reminder, next month we're off. We'll be at the AACR meeting, so we hope to see you all there. And then we'll pick up in May with Dr. Lee Ellis from Cedars-Sinai, who will give the May lecture. So thanks again, and have a great rest of your day.
Thank you, everybody.